Introduce the first speaker of today, which is Jean-Francois Babadjian from Paris. And he will talk about uniqueness and the characteristic flow for a non-strictly convex singular variational problem.
Good morning, everybody, and thank you very much for the presentation and for the invitation. I'm really happy to be here in Pisa. So I'm going to speak about not that recent work in collaboration with Jean-Francois, so about uniqueness issues in specific problems of the calculus of variations coming from, so with motivation coming from the theory of plasticity. So I will not insist a lot about the model and the modeling, and rather maybe on the technique, on the method that we use for addressing these type of problems. So the starting point, which is totally disconnected from plasticity, is a minimization problem, which is precisely in between two very well-known problems in the calculus of variations. So the first one being the minimization of the Dirichlet energy, integral of 1/2 of grad u squared, and the other one being the minimization of the total variation, so the integral of the modulus of the gradient of u. So I should have started to say that the problem is in the following setting. So my unknown is a function u, which is defined in R2, and which is scalar valued. And what we did, unfortunately, doesn't seem to generalize to any other situation, dimension n here and vector value function. So this is really a two-dimensional scalar problem. So these are two very well-known problems in the calculus of variation, and the one in which we are interested is in between, in the sense that we are minimizing an integral functional f of grad u, okay, where f is precisely, so where is it written here, the minimum between 1/2 of grad u squared and the modulus of grad u. So it's a function, it's a functional which is essentially the integral of the minimum of the two integrands. So I'll tell you in the next slide why we do that. It's not just for pleasure, it's because we have motivation behind it, which is coming from plasticity. And written like that, this problem seems to be a very standard problem in the calculus of variation. So you minimize an integral functional. Unfortunately, so this is a plot of the graph of f. You can easily see that this function is non-convex. You have the quadratic part here, and then it goes to a linear part, but you have a non-convex region here. And when you minimize a non-convex function, you usually don't have, in this scalar setting, you usually don't have lower semi-continuity of your functional, and you need to relax it in order to be able to look at the behavior of minimizing sequences. So there are two steps in the procedure of relaxation in our setting here, because first of all, you have oscillation effect. So I think I don't need to describe much further this type of effect. So you can make gradient oscillate very fast in such a way that your functional here will reach values of the energy which are strictly lower than the value of f. And all the values that you can reach by doing these fast oscillations of gradients are all the values of the convex hull of the function f, which I denote by f star star. Okay, so oscillation effect of gradient make it possible to reach lower values of f given by the convex hull, by its convex hull. And in this very specific situation, you can explicitly compute the convex hull, f star star of z. So it has this expression, so it's easier to see it on the graph. So you still have this quadratic part, 1/2 of z squared close to the origin. And then in order to get the convex hull, you increase your argument z as long as you get a slope equals to 1, because the slope of the modulus of z is 1. And then you depart from the graph of the quadratic functional with a slope 1. So this is the reason why you have to translate a bit here by this constant 1/2. and this is symmetric, so get exactly the same graph on the other side. So this is the expression of f star star, and this is this plot. And we are essentially happy because this convex hull computation deals with the fast oscillation effects. Unfortunately, this infimum is, so you still get an infimum here. Because so there are not only oscillation effects, there are also concentration effects due to the fact that our function f and its convex hull as well have linear growth at infinity. So it leads to possible concentration effects of gradients, which means that gradients can become measures instead of being just L1 functions. And so in order to account for these concentration effects, you have to extend your functional to the larger space BV instead of W11, which accounts for possible gradient measures. So you have to add to this energy a singular part, which takes into account the singular part of the measure gradu. So NabLaU here means the regular part of the gradient of the measure, and DSU is the singular part in the Lebesgue decomposition. And with this, we are essentially happy. We took into account oscillation and concentration effects, and provided you apply suitable boundary condition, external loadings in order to make the minimization problem non-trivial, let's say, you get existence of solutions to this problem. Existence, but in general, non-uniqueness, because you have a strictly convex part here for the energy, but you have a non-strictly convex part here, which prevents, in general, to get uniqueness. And non-regularity, because you are in BV, and BV is not regular. Okay, so this is a rough presentation of the problem we had in mind. And what was the motivation behind this problem? So the motivation came from Encke plasticity, from plasticity. Actually, this was our starting point that I rephrased in the first slide in order to make it maybe more understandable. So the connection between this variational problem and plasticity comes from the fact that there is an alternative way to compute the convex hull of the function f. So I recall you the expression of f, so the minimum between the quadratic functional and the linear functional. And an explicit computation makes it possible to compute the convex hull directly. But there is another way to do it by observing that when you want to compute the convex hull of the minimum of two convex functions, let's say, there is an operation which is called infimal convolution, which allows you to do that. And the infimal convolution between these two functional is exactly the expression which is written here. It consists in minimizing the sum of the two functions, so 1/2 of the modulus squared and the modulus, among all arguments, sigma and p, whose sum is equal to the argument of f star star. Okay? Well, so this is the inf convolution between these two functions. This is just a name that we give because here everything is explicit, so we can do it by hands. And you can check, this is an exercise, not difficult, that when you compute this minimum, you exactly get the same expression than the one which is here. So what is the advantage of doing this? It has the advantage that we can rephrase these variational problems, which depends just on one variable, which is u, into another variational problem, which is the same, which is equivalent, which has now three unknowns. So u as before, but also a variable which represents sigma here and p here. So I will tell you in a second why I'll call them sigma and p. And so the previous minimization problem, so if you formally replace f star star of grad u by this expression, among all pairs sigma and p whose sum is equal to the gradient of u, the previous variational problem which was written here is exactly equivalent to this one. So you now minimize the sum of the integral of sigma squared, okay? So sigma and p are a vector in R2, right? Because the gradient of u is a vector in R2, so sigma and p as well. So you minimize the sum of the integral of sigma squared plus the variation of p. among all triples U sigma P, such that sigma plus P is equal to the gradient of U. So this is exactly the same problem that we have just rephrased. Maybe it looks more complicated like that, but actually it's a way to interpret the problem which will be convenient for us for what we wanted to do. Okay, and the functional setting, the natural functional setting is looking for sigma in L2, because here I have the L2 norm of sigma. U is still in BV, as before. And since P is the difference between the gradient of U and sigma, P should be a measure. Okay? And in order to make this problem non-trivial, as usual, you need to impose the suitable boundary conditions and so on. So this is exactly a problem of plasticity. So in mechanical language, U stands for a displacement. So maybe I will use this terminology in the sequel. So U is a displacement. Sigma stands for a stress, and P stands for a plastic deformation. So this is the reason why I use this type of notations. So now I will make the problem a bit more precise. So I am still in R2. Omega is a smooth open set in R2. And I partition its boundary into the union of gamma D and gamma N. On gamma D, I will impose a Dirichlet boundary condition, W. And on gamma N, I will impose a Neumann boundary condition that I call gamma. And I need W to be at least in L1 and G to be at least in L infinity. Okay? And so with this boundary condition external loading, the real variational problem I'm considering is the following. So I minimize exactly this functional among all triples U sigma P in this space, such that the gradient of U is the sum of sigma and P in omega. So I have here to remove a linear term related to the Neumann condition, so minus the integral of GU on gamma N. So this is the Neumann condition. And usually, when one imposes a boundary condition, one should, a Dirichlet boundary condition, one should impose U to be equal to W on gamma D, on the part on which I impose this. The point is that here we have a variational problem in a BV, in a space where you allow discontinuities. And since you allow discontinuities, you have to allow discontinuities on the boundary as well. So in particular on the Dirichlet boundary. So you should allow U to not attain its boundary value on gamma D. So this is very classical in variational problems in BV. And this has to be taken into account. So this is taken into account in the following way. So P, which is a measure in omega, I consider it as a measure on omega union the Dirichlet part. Okay, I impose P to take this value, so on the Dirichlet part. So the difference between the prescribed value and the actual trace of U times the outer normal of the boundary. And I have to pay it energetically by putting a term which is here, which is hidden, which pays for the jump on the boundary. Okay, so this is very important in our problem to have in mind that although we impose Dirichlet boundary condition on some part of the boundary, it can even be on the full boundary if you want. It might be energetically convenient to jump on the boundary and so that the boundary condition is not satisfied. And this is one of the main difficulties for the issue that we have to deal with uniqueness of this type of problems. Okay. So this is our our starting point, let's say, our original starting point. And so you can use standard methods to prove that you do have existence of solutions in this energy in the energy space, which is this one. And this is a convex variational problems. So the minimization is equivalent to the Euler-Lagrange equations, which I will describe now, which is this set of PDEs. So I will write this Euler-Lagrange equation on the board because to have it in mind along the talk. So the first equation is just rewriting that the gradient of U is equal to the sum of sigma and p, okay? Then the second equation is what you obtain when you do variations only with respect to sigma. So you get that sigma should be a divergence-free vector field in omega, and its modulus. So the modulus is so this is a Euclidean norm here. This is important to be the Euclidean norm. Should be less than or equal to 1. This is what you get when you do small variation with respect to the variable sigma by taking gradients as competitors. And then you get this equation here, which is in mechanical term called flow rules, which tells you that sigma scalar product with p should be equal to the modulus of p. So this should be in omega union gamma d. This is in omega. And this is the equation that you get if you do variation with respect to p only. Okay? This one is just rewriting the boundary condition in this relaxed way. So p should be equal to the difference between w and u times the normal on gamma d. Okay, so this is just rewriting this equation here. So this is the relaxed boundary condition. So it takes into account the fact that you are allowed to jump on the boundary. And the last one is the Neumann boundary condition, which is related to this term. This is the set of equations that should satisfy the solutions to this minimization problem. And being solution of this is equivalent to solving this minimization problem because of convexity. So there is a technical issue I don't want to describe too much, is that this product is usually not well defined in the standard way because sigma is just L infinity and P is a measure. So you are not allowed to do this product, but you can give a weak sense to this product. But I don't want to enter into this type of details, unless you have questions on that. Okay, so maybe I can detail a bit this condition. So this condition formally tells you that either, so you have two situations. If sigma, if the modulus of sigma is strictly less than 1, so this equation will tell you that necessarily p must be equal to 0. Okay. And if on the other hand sigma has modulus equal to 1, this equation will tell you that p will be equal to sigma times the modulus of p. Again, this is a formal way to rewrite this equality, because I'm not allowed to write this product, but roughly speaking, this is the situation, and I can decompose this equality into two equalities, one in omega and one on gamma d. So in omega, this tells you that p and sigma are parallel to each other. Okay, and in gamma d, it tells you that sigma dot nu times w minus u is equal to w minus u. This is in gamma d. This is, let's say, a formal way to rewrite this equation in omega or on the Dirichlet boundary. Okay. Okay. So behind this system of equations, there is a, okay, hidden, I don't know, but there is a hyperbolicity structure only with respect to spatial variables. So here there is no time, okay? This is just a set of equations depending on spatial variables, but these equations turn out to be hyperbolic. And in order to highlight this hyperbolic structure, so I need to introduce several objects. So first of all, this is just an observation. From the point of view of uniqueness, the stress sigma is unique. I mean, when you have two solutions of these variational problems or of these Euler-Lagrange equations, the sigma must be unique. This is essentially due to the fact that you have a strictly convex energy with respect to sigma. Okay, so sigma is unique, and there is a regularity result going back to Bensuso and Fraser, which tells you that so in the energy space sigma should be null infinity, but actually you can do better. It belongs to H1 log. Okay, so this is not an observation which will have some importance later. So coming back to hyperbolicity, I need to introduce this object, which is sometimes called by mechanicians plastic multiplier. So this is a measure mu, which is the sum of the variation of P and the Lebesgue measure. And if I write, I use the equation, so the decomposition of the gradient of U, which is written here, as well as this flow rule, which is here, I observe that I can rewrite the gradient of U as sigma times mu, because I'm using this equation here, that P is equal to sigma times mod P. So when I replace P by this, I get sigma times mu. And then just writing that the curl of a gradient is 0, or the divergence of a rotated gradient is 0, I get the following continuity equation, that the divergence of sigma perp times mu is equal to 0. Okay, so mu is this measure, and sigma perp is just the rotation, the pi over 2 rotation of sigma. So if you give yourself sigma, which is unique, mu, the plastic multiplier, should solve this continuity equation. And to this continuity equation, you can associate characteristic curves, which are, provided they exist, solutions to the following ODE, gamma dot equals to sigma perps of gamma. And then you should expect that along these characteristic lines, your solutions, mu, should have some good properties. Unfortunately, right now, we don't have enough regularity, enough information on sigma to give a meaning to this equation. Because the only information that we have is H1 regularity of sigma, or sigma perp. And this is unfortunately, so we are in 2D, so H1 doesn't embed into some space, in some good spaces. But we don't have enough regularity to give a meaning to this ODE. Even in the sense of Lagrangian flows of Di-Pernalions or Ambrosio, because what is missing to apply this type of theory is a control of the so-called compressibility constant, which is the divergence of the vector field. So the divergence of sigma perp, which is the curl of sigma. So usually in this type of theories, one needs to control, roughly speaking, the L infinity norm of that quantity, or the positive part or negative part, but we have no information at all on this. So this prevents us to use this theory, and we have to do it. We have to do something else. Okay. So before going forward, I would like to present you an example, a counterexample of non-uniqueness and non-regularity of solutions of this system when I have mixed boundary conditions. That is a Neumann condition on one part of the boundary and a Dirichlet condition on the other part of the boundary. So the example is the following. So my domain omega is this trapezoidal set, okay? So which is written in an analytic term here. So here I have the straight line x plus y equals 2. So on the vertical part, I impose Neumann boundary conditions. So gamma n is the union of the two vertical parts. And the horizontal part and this line here correspond to the Dirichlet part gamma d. And so I impose this Neumann condition and Dirichlet condition. And then, so I will not do the computation because it's quite boring, but you can solve it explicitly by hands. You can find all solutions by hands. So sigma, which is unique, this is always the case, turns out to be homogeneous in space. So it is this vector, 1 over square root of 2, 1, 1. Okay, so that's it. By the way, its modulus is always equal to 1. It's never, because the modulus of this vector is always equal to 1. And the displacement u is all the displacement u solutions of this problem is given by this function, x plus y plus a function z of x plus y divided by square root of 2, where z is a function which has the following shape. So the argument of z is x plus y, okay? So when x plus y, when x and y belongs to this gray triangle which is here, which means that x plus y is between 0 and 2, 0 and 1, sorry, the function z should vanish. So in this gray part, this term disappears, and you have a unique solution, which is x plus y divided by square root of 2. And on the complementary part, the set that I called U here, the white set here, z should be a non-decreasing function going from 0 to the value 0 here to the value 2 on this line. And the point is that it can be any non-decreasing function. So you can have a smooth function, you can have a step function, you can have a contour function if you like. So this tells you that you have a drastic non-uniqueness because you have as many solutions as such a function z, and you have non-regularity because you can put any type of BV function that you want. So why do we have uniqueness in this gray region, which is here? The reason is that, so u is a function of x plus y. It's a function of x and y, but more than that, it's a function of x plus y. And when you look at all the straight line, x plus y is equal to a constant. So you get all straight lines like that parallel to this boundary. And if this straight line passes through a point in this gray triangle, it will necessarily intersect the Dirichlet boundary here transversally. In other words, it will catch the Dirichlet boundary condition, which is here. And since the function u is constant along all these straight lines, it will propagate the value of the boundary condition inside. So this is exactly the characteristic method in hyperbolic PDEs, which gives you exactly the value of your function inside the domain by propagating the information on the boundary. And this argument, unfortunately, doesn't work on the gray part, which is here, because all straight lines x plus y equals to a constant will only intersect these two vertical parts of the boundary, which are Neumann parts, on which you have not prescribed anything on the displacement. So it gives you a lot of freedom to put essentially everything that you want on this part. So to summarize, this counterexample tells you that in the case of mixed boundary condition, by which I mean when you have Dirichlet condition and Neumann condition, you can not hope uniqueness and regularity. So the problem is over in that case. And so now, starting from now, I will only consider the case of Dirichlet conditions. So I will assume that there is no Neumann part. And look what happens in that case. So from now on, so I assume to have only Dirichlet boundary condition. So our objective was to try to make this kind of argument more general, let's say, which we partially achieved, partially because we need to do some assumptions at some point. And this is what I'm going to try to explain you. Okay. So this is our setting. So now we consider this problem of plasticity with a pure Dirichlet boundary condition. Okay. In order to go forward, so as I tried to explain you when I introduced this notion of characteristic, we are stuck by the lack of regularity of sigma. So one objective is to try to improve the regularity of sigma going beyond the H1 log regularity of Bensoussan and Fraser. To do that, we used another regularity result due to Seregin, which gives you some kind of partial regularity result. So in elliptic systems, So you usually don't have regularity of solutions, but you do have partial regularity. So you can you can define sets by means of densities, which corresponds to open subset of your domain of full measure on which your solution has a better regularity than the one which is expected by variational methods. If you perform exactly the same type of techniques, and this is what did Seregin, you end up with an open subset omega 0 of omega, which unfortunately doesn't have a full measure in omega. It is what it is, but on which you have better properties. So here, the better properties provided by Seregin tells you that in omega 0, which is an open subset of omega, the stress sigma has modulus strictly less than 1. So according to the observation I did before, this tells you that necessarily P should be equal to 0. And if P is equal to 0, sigma should be the gradient of U. And if sigma is the gradient of U, you replace it, you get that U is harmonic. So the set provided by Seregin, which might be empty, by the way, tells you that on that set, U is harmonic. And as it is harmonic, it is as smooth as you want. So this is a very good starting point from the point of view of regularity, at least. From the point of view of uniqueness, this is good, but it doesn't close the question, because indeed, U is harmonic in omega 0. And even if omega 0 touches the external boundary of omega, since you a priori do not satisfy the boundary condition on the boundary, you might not have uniqueness on omega 0. So I forgot to say that this result of Seregin is an interior result. It's not a result which goes up to the boundary. So although the function U is smooth in omega 0 and harmonic, the fact that you do not necessarily prescribe the information on the boundary prevents, in general, to get uniqueness in that set. So this is what happened in that set. So this is good. And on the complementary, almost everywhere, sigma should have modulus equal to 1. Okay. And here come our main assumption, which, if I have time, which is not sure, I will comment in the end. So omega 0 is a set given by Seregin. So I consider omega the complementary of, so this is omega r. I consider the complementary of omega 0, and we assume, so this is an assumption, that the complementary of that set, omega minus omega 0, is a convex set. So this is omega 0, and this is the complementary of omega 0. Okay, it's a so this is an assumption. So what motivates this assumption is that, of course, we try to find examples, counterexamples to this type of problems. And up to a few weeks ago, we were unable to find examples for which this set was not convex. So we did this assumption. So with this assumption, we can split omega into the union of three sets. So omega 0, omega 1, which is the interior of the complementary of omega 0, and the common boundary between these two sets, which I call sigma. Okay. And we distinguish now two cases related to the fact that omega 1 is empty or not. So in the first case, so if omega 1 is empty, which means that the complementary of omega 0 is as empty interior, there are two possible situations. Either there is no omega 0 is omega, which means, according to what is written here, U, so P is 0 everywhere in omega, not in omega bar, and U is harmonic in omega 0, in omega, or omega minus omega 0 is precisely a straight line segment which separates omega into two subsets. And so in that case, you can solve separately this equation in these two subsets that I call omega plus and omega minus. and you get essentially these properties. The point is that although in both cases the solution is essentially smooth, possibly outside a straight line segment, it might happen that the boundary condition still is not satisfied. So P is 0 in omega, but it is not necessarily 0 in omega bar, on the boundary of omega. So consider this first situation, for example, that you have a harmonic function in the full omega. You have a harmonic function, but whose trace on the boundary is not necessarily prescribed, and this might prevent uniqueness. But in spite of this, we are still able to show that you do have uniqueness of the solution. So in this first case, when the complementary of omega 0 has empty interior, we are able to show uniqueness of the solutions, u sigma p of this problem, and essentially regularity, because either u is smooth everywhere, or it has just a discontinuity set which is made of one segment which separates your set into two subsets. Okay. And then it remains to consider the more difficult case where the complementary of omega 0 has non-empty interior, so which means that omega 1 is non-empty. So you do have here a convex open subset which is non-empty, which is in the complementary of omega 0 and its boundary. And in this set, we have a more precise hyperbolic structure. So let me recall you what we have at hand. So we have the stress field, sigma, which up to now is only an H1 log function in omega, so in particular in omega 1 as well. And you have this plastic multiplier, so we call you what it is. This is this plastic multiplier, which has the property to solve this continuity equation. Actually, this continuity equation is solved in omega, but here I focus on what happens in omega 1. But now in omega 1, I have better information for sigma. Sigma is still a divergence-free vector field. This doesn't change. But now in omega 1, it has modulus equal to 1. In omega, it has modulus less than or equal to 1. But in omega 1, essentially by definition of omega 1, it has modulus equals to 1. And this type of equations, this equation is very well known from people in the community of micromagnetism. What I call sigma is usually called M because it's a magnetization. It's a divergence-free unitary vector field. And many results are available for this type of equations. In particular, results coming from De Simone, Ecole, Muller-Otto, Jabin, Otto-Pertam, which tells us that when you have an H1 log solution to this equation, actually the solution must be locally Lipschitz. And more than that, it should be constant along straight lines, orthogonal at its points to sigma of x. So maybe I'm going to do a picture. Here. I'm not going to do a picture. So you have omega 1. So this is omega 1. You take a point, x in omega 1. No, but that's okay. That's okay. Thank you. You take a point in omega 1, and you have sigma of x, which is a vector in omega, a vector of modulus 1. And you look at the straight line which passes through this point and which is orthogonal to sigma of x. So this is what I call Lx with this notation. And the result of all these people tell you that sigma is constant along all these straight lines. Okay, and then you can do it at each point of omega 1. So from the point of view of sigma, okay, we have many informations coming from all this theory, and we are quite happy because actually these characteristic lines correspond to the solution of this ODE in omega 1. So in omega 1, the characteristic lines are straight lines. Okay, so from the point of view of sigma, we are happy because we have nothing to do, essentially. From the point of view of u, we need to work a bit more. And what we proved with Jean-Francois is some kind of rigidity result, which tells you that the displacement, so U, is constant in omega 1 among almost every lines, which is written in this maybe complicated way. And maybe I have I can do a sketch of proof of this argument, a formal proof of this. So formal because the operation that I'm going to do is not allowed because my function U is only BV. So let us look at U on such a characteristic line. So X plus T sigma perp of X. So this is U on this straight line Lx. So I want to prove that U is constant along this straight line. So I take the derivative with respect to T. So I apply a formal chain rule, which I'm not allowed to do, but I do it. So this is a gradient of U at the point X plus T sigma perp of X dot sigma perp of X. Okay? And then I will use the fact that sigma is constant along this straight line. This is what this result tells me. So this is the gradient of U at the point X plus T sigma perp of X dot sigma perp of X plus T sigma perp of X. Right? But now I have to use what I just canceled, that the gradient, thanks to this equation, the gradient of U and sigma are parallel to each other. So gradient of U times sigma perp is equal to 0. So this is a formal argument. And of course, you need to work a bit to make this argument rigorous because of the lack of regularity of the gradient of U. So this is a rigidity result, which tells us that we have information not only on sigma, but also on U, on these straight line characteristic lines living in omega 1. How much time do I have? 5 minutes. Okay. Oh, okay. Okay. So, okay. So you stop me at some point. You just stop me. So thanks to this type of properties, we can show that this set omega 1 has a precise geometric structure, which is of the following type. So if you take two characteristic lines in omega 1, so what I draw here is omega 1. Okay? You forget about omega 0. It is this set here. Okay? So you take two characteristic lines, and the first situation is that the characteristic line intersect each other on the boundary. And in that case, we can show that all characteristic lines inside the zone delimited by Lx and Ly must pass through the same point, and it gives you what we call a boundary fan, which is in micromagnetism language a vortex. Okay? And because using the fact that sigma and U are constant along all these straight lines, we can essentially solve this system of equation in polar coordinates. And what we get is that sigma is a vortex centered at z hat, this intersection point. Alpha is -1 or +1. It gives you just the orientation of the vortex. And U, the displacement, is a monotone function of the angle. Okay. So I consider this set, this fan, as open sets, and I take its union. It gives me the union of all possible fans in omega, and I denote by C the complementary of the fans. And this set C can be described in the following way. So if I take a connected component of C, if it has empty interior, it must be just one characteristic line, one segment. Or if it has non-empty interior, it must be of one of the following type. So either it is a subset of omega 1 delimited by two characteristic lines, and all the characteristic lines in between do not intersect each other. Or it is a subset of omega 1 delimited just by one characteristic line, and all the characteristic lines in that set do not intersect each other neither. But what you can quite easily imagine is that you have a family of straight lines, okay, which do not intersect each other. At some point, they should become tangential to the boundary. Okay. And this set of points where, in quotation marks, the characteristics are tangential to the boundary are what we call the characteristic boundary, DC of C, and which is precisely defined here, but I don't have time to comment it. And we prove that this characteristic boundary, the set of the characteristic boundary, DC of omega 1, is very small in the sense that it has at most two connected components, which are closed straight line segments, possibly reduced to a single point. This is exactly what happens here. The characteristic boundary here is just one point. Okay? But if you imagine that omega 1 has a flat part on the boundary, it can be exactly this flat part. And because of convexity, you have at most two connected components of this characteristic boundary. And more than that, sigma turns out, so using all this set of equations, turns out to be a continuous function in omega outside a subset of this characteristic boundary that I call Z, which is made of at most 2 points. So what happens is, okay, I don't have time to comment about that. This is an improvement of the regularity of sigma because we pass from H1 log regularity to continuity in omega up to possibly 2 points. So Z is at most 2 points. And this is actually enough to give a meaning to the solution of the ODE. So here I assume to simplify that the exceptional set is empty. If not, it's only 2 points and you can essentially consider the different situation by hands. So by continuity of sigma, so I can now solve this equation. So I have existence of solution to this ODE by Cauchy-Peano, but not uniqueness. Although we have piecewise uniqueness because sigma is continuous in omega, but it's locally Lipschitz here, sorry, and here it's smooth. So what happens is that it's just at the interface sigma between omega 1 and omega 0 that you lose Lipschitzianity, essentially. But still, you can solve this equation. And once you have solved this equation, you can essentially apply the characteristic methods to show that under this assumption of convexity of omega 1, of course, okay? In the case of pure Dirichlet boundary condition, you can reach uniqueness of the solution in the whole of omega. So from the point of view of regularity, so sigma is continuous, okay? And we can show a partial regularity result for U. So U is just a BV function in general because it is the energy space. It's smooth in omega 0 because it's harmonic. And we can show that it is continuous in the portion of omega 1, which are swept by characteristic coming from omega 0. So I didn't write explicitly the statement, but this is a partial regularity of U in omega 0 union the portion of omega 1 where the characteristics are coming from omega 0. Okay, this is a sketch of proof, so I don't detail it because I'm just on time. So open questions. So of course there is this convexity assumption on the complementary of omega 0 that we were not able to either to prove nor to neither to prove nor to do something to find an alternative proof. So I just have to say that we were really convinced that in general the complementary of omega 0 should be convex. Up to a few weeks ago, convinced because we really tried to find examples, counterexamples, and every time we found convexity of the complementary of omega 0. Just a few weeks ago, we only find a counterexample of the convexity. So in general, the complementary of omega 0 is not convex. So we have two counterexamples, one analytical, where we do computation at nth, but in that case, in that analytical case, we find that the complementary of omega 0 is made of two convex sets, well separated to each other. And in that case, we can reproduce our argument quite easily. And the other example that we have is a numerical example for which it seems, so this is a numerical example, so maybe we are not interpreting well what we see, but it seems that the complementary of omega 0 is a finite union of convex sets which intersect each other. And in that case as well, we can reproduce our argument. So, in general, we do not have convexity of the complementary of omega 0, but it seems that our method is enough stable in order to consider the counterexamples that we found. Okay, and there are other open questions related to the fact that here I presented you a static problem of plasticity, while it should be an evolution problem. So that would be an interesting issue to go to the evolution problem. And finally, this is a very simplified model because I'm considering scalar value displacement, while in mechanics one should consider vector value displacement. And this is also something that should be interesting to address in the future, at least in the 2D vectorial case, for which we have some paths to follow in order to adapt this type of methods. So I am almost on time. Okay, so I stop here and I thank you for your attention.
So thank you for the very nice talk.
Thank you.
Are there questions? Yeah.
Regarding the convexity, I mean, shouldn't your proof work locally at least? And couldn't you then start, if it was non-convex, try to glue things together?
Well, okay, the point is that once you have a non-convex part, this is a technical issue related to the definition of what I call the characteristic boundary. So the part of the boundary on which the characteristic becomes tangential. So when you are convex, we can define it pretty well. When you are non-convex, it's not clear how to define it. And this characteristic boundary plays a very important role, starting from the regularity issues, which is the starting point of our analysis. We need to prove additional regularity to solve the ODE, to perform the characteristic method. So this is a matter of definition of the characteristic boundary for non-convex sets, actually.
Okay.
I'm not saying that it's impossible. It's just we didn't succeed.
Okay, thank you.
Other questions? So maybe I have a small one.
You're a nice chairwoman.
Okay, I just didn't want to ask two questions right now. So where do you need R2? Is it because you solve your characteristics and your in 2D your characteristics already cover the entire if you that picture behind you with the normal in higher dimensions you would have a plane, right? And then your characteristics go bad, or what happens?
So in higher dimension I should consider a vector valued problem. This scalar problem doesn't make sense anymore in vector valued in the vector valued case. From a mechanical point of view, then you can address it from a mathematical point of view. So in the vector valued case, in the 2D vector valued case, so you have two families of characteristics instead of one, which are not necessarily straight lines in omega 1. You do what would be the equivalent of omega 1. This is a so-called Encke-Prandtl net, which means that these two families of characteristics intersect at each point with a pi/2 angle. And you have some equations that should be satisfied by sigma and u, which are more complicated than in the scalar. In the scalar case, the equations are U and sigma are constant. In the vectorial case, you have that some components of U and sigma should be more or less constant among this one of the characteristic of one family. So you have a similar properties, but more complicated to address.
So going to vectorial is more interesting than going to higher dimensions, but scalar is your.
No, I'm saying that so there are two possible. If I do higher dimension, I should do vectorial.
Yeah, that's okay.
But even in a 2D vectorial,
yeah, sure,
it is difficult.
Sure.
It is more difficult.
Sure.
I have a small question. So if I understood correctly, you said that you in general you don't attain boundary conditions.
Yeah.
But if you assume omega to be convex, a very nice boundary conditions, can you say something?
Yes, I think that if omega satisfies the bounded slope condition, and if you have a boundary condition which is maybe C1, you should satisfy the boundary condition everywhere on the boundary. But we have no assumption on omega, and our boundary condition is just L1. And in that case, so in general, you don't achieve the boundary condition everywhere on the boundary, but we can prove, and this is part of our uniqueness proof, that you always attain the boundary condition on the portion of the boundary of positive measure. So it's not possible to not attain the boundary condition everywhere in the boundary.
Thank you.
Thank you.
So if there are no other questions, we thank Jean-Francois again.
Thank you.
Okay, so the second speaker is Manuel Friedrich from Erlangen, and he will talk about dimension reduction for elastic materials with voids.
So, thanks very much, Roberta, for the kind introduction, and thanks very much to all the organizers for having me and for setting up this wonderful workshop. Today I would like to speak about recent joint work with two former postdocs of mine, with Kostas Zemas, who is now in Bonn, and with Leonhard Kreutz, who is in Munich. So my talk is about something which is in the realm of so-called stress-driven rearrangement instabilities. That's about morphological instabilities of interfaces between elastic faces. And this phenomena are generated by an interplay of two forms of energies, namely elastic energy and surface energy. So there are a variety of phenomena which is under this umbrella. For instance, delamination and fracture. There is a theory on the growth of crystalline thin films. And the third point here on my list is the one that I would like to focus on today. So you have an elastic material, but inside of this elastic materials, you have the formation of material voids that you can see here in black. Now let me start on the next slide with my variational model. So my variation model is like this. I still have a void set, which is now depicted in red, and it should in general be a C1 set. Then I also have a reference configuration omega, and I have a deformation, which is defined here, and it maps the material in the reference configuration to a deformed configuration. It's important to mention here that the deformation should be Sobolev, but it's not defined on the entire omega, but just in omega without the void set. So there is nothing in the void set. And then I write down an energy, which is of elastic and surface type. So here on the right-hand side, you see the surface energy. That's in the simplest case, just measuring the area of the boundary of the void, which is inside of omega. Okay. And on the left-hand side, I have the elastic energy. So that should be something which depends on the gradient of the deformation, measuring the local distortions in the material. And now for this elastic energy, you have different possibilities. Today in my talk, I will pick nonlinear elasticity. We heard about that already yesterday in Ricardo's talk. So in particular, I will assume W to be polyconvex. And another important property is frame indifference, namely the density is invariant under rotations. You see it a little bit more precisely here in the assumptions that I also assume, namely the minimizers of W are exactly the set of rotations. And I also want to assume a quadratic growth out of this well. So if you want, you can consider W to be proportional to the squared distance of the deformation gradient from the set of rotations. Okay, and the problem I want to solve is a minimization problem. If you want, you can have boundary conditions on a part of the boundary. You could also have boundary or body forces, whatever you want. The important thing for me in this minimization problem that I'm considering, it's a minimization in both variables. So both in the deformation and in the void set. In this sense, it's a free discontinuity problem. And this is a hard problem because in principle, you don't expect to have minimizers because you have problems both with compactness and with lower semi-continuity. So why is this? Well, first of all, bound on the perimeter has no good compactness properties for C1 sets. You should relax this assumption and work with sets of finite perimeter. And then the right notion is here to work with the reduced boundary. Well, if you have this, then what do you do with the Sobolev function? I mean, if E is not regular, then omega without E, maybe it's not an open set, so you cannot really work with Sobolev functions. So you do a little trick. And the trick is that you extend the function in an arbitrary way. I take the identity inside of the void. Then I get a nice function which is defined on the entire omega. But this comes at a price, namely usually and typically I introduce jumps at the boundary here of the void. My notation for this is J of Y. And this is the reason why after this extension, I have to work with SPV functions. Well, that's how the relaxation should look like. It takes these two parts of the energies into account in terms here of the reduced boundary for the void. And here the elastic energy should depend on the gradient of an SPV function. Well, unfortunately, or I mean, also maybe interestingly, there is another term coming up in the relaxation. And this is the term here on the right. How come? Well, imagine you have a minimizing sequence, and along this minimizing sequence, a void collapses onto a jump, a crack, which produces discontinuities of your deformation field, and this is what you see here. Why do you see this prefactor 2 here? Well, again, look at my hands. I mean, if this is the void which collapses, you have a part which is coming from up and a part which is coming from below, so you need to count the boundary twice. What are the typical or the most important ingredients of the proof? Well, I said that already. You have to work with SPV functions and with the theory of sets of finite perimeter. For the lim-inf inequality, slicing is a good thing to do. So you reduce the problem to 1D. And this in particular will tell you that you can pick up the 2 here. Because if you reduce the problem to 1D slices, you get a 1 if you enter the void, and you get a 2 if you exit the void again. So this is a good method in order to see this prefactor 2 in the relaxed problem. And then there is a special thing that you need to do for the recovery sequence. In particular, you would like to construct recovery sequence under this additional assumption, which means that the area of the jump is related to the Minkowski content. So why is this important? Well, in the limit, you can have a jump here in black, but along your recovery sequence, no cracks are allowed. You have to make everything to a void. Only voids are allowed along the original problem. So you make a crack a void by just taking the row neighborhood. Here you see it in red, and then you need this property in order to make the recovery sequence work. And as you might know, I mean, in general, for SPV functions, this property doesn't hold. This regularity property for the jump, but then you work with a density argument. By a density argument, you can assume this, and then you do the typical diagonal argument in the theory of gamma convergence. Okay, that's an old story, basically. I mean, this paper that I was describing here is by Braides, Chambol, Solchi almost 20 years ago, but it's still kind of the starting point of what I would like to do today. Today, I would like to combine this problem with dimension reduction. So from now on, I'm looking to a thin plate, which has a cross-section H, S and a height h, and the energy looks as before. So the only thing that I do, I rescale here the energy in terms of 1 over h. This I just do because that's the area or the volume of the thin plates. So I need to do that in order to get something non-trivial if I pass to the limit h to 0. Then is there a second rescaling that you see here in red, 1 over h beta. H to the beta gives you the typical energy per unit volume. And it's well known already in the elastic case that depending on the choice of beta, you get a hierarchy of different limiting 2D models. So I'm on this slide, I'm not giving you all the references on dimension reduction. I wouldn't have space for that. I just give you some results which are available in the setting of voids and fracture. And there are some linear models, including also works by Jean-Francois. I'm not talking much about linear models because my talk is more about a nonlinear setting. So there are some results in the so-called membrane regime. The membrane regime is the regime where beta is equal to 0, so you have here prefactor 1. There are some results, much less is known in the setting where beta is positive. To the best of my knowledge, there are actually just 2 results in this setting due to Bernd-Schmidt. One is from 2D to 1D, and the second one, which is more in the spirit of my slide here, where you go from a 3-dimensional thin plate to a 2-dimensional plate, is a joint work of Bernd-Schmidt with his former postdoc, Mario Santilli. Okay, so that's basically the literature which is known for dimension reduction with voids or fracture. And so the goal of my talk today is that I would like to revisit this result that I just mentioned. And we'll revisit this by considering the same model, but under more general assumptions. And I will come to that later in my talk. I also want to show you that the approach is flexible. I mean, you can do other things. You can also go from 3D to 1D. That would mean that you have a thin rod, which effectively in the dimension reduction limit should be described by a 1-dimensional curve. This is the outline of my talk. So I assume that many of you know the story of Friedrich James Müller, so what has been done in the purely elastic case, but I will still revisit this also to settle the notation and to give you again the main ideas of their approach. After that, I will come to the formulation of our results, and I will particularly also tell you how this is related to what has been done by Santilli and Schmidt. And then in the second part of my talk, I will come to some of the ideas in the proof. All right, so let's start with the elastic case. So no voids anymore, just elastic energies in Sobolev spaces. And well, the first thing that you always do if you talk about dimension reduction, you start with a deformation on the thin domain, and you replace it by a deformation on the thick domain. The notation for the thick domain is omega without an index. It has height 1. And you do that by doing a rescaling in the third variable. Okay, that's very classical, and you also need to come up with the corresponding notion for the gradient. You get a rescaled gradient. So sometimes on my slides you will see the index h, but that's not important. That's just coming from this rescaling. Okay, so also the energy you rescale from the thin domain to the thick domain in terms of this rescaled deformation. You see that the rescaling factor from the volume is gone. And I'm just keeping the red one. And this is now telling me which kind of scaling I would like to consider today. This exponent here is what was before beta. So I'm considering beta equal to 2. And this is the so-called bending regime or the so-called Kirchhoff regime. So that's what I'm considering today. Okay, then you want to send h to 0. And before I come to the gamma limit, let me tell you what is known about compactness. So what's the compactness result? Well, you take a sequence of energies with sequence of deformations with bounded energy. And then in the limit, you identify a limiting deformation y, which has the following properties. So first of all, the gradient of that is always a rotation. Pointwise, that's not really surprising. Remember that I have a rescaling here. So this prefactor blows up, and W is exactly minimized at the set of rotations. So that's a natural consequence that you get. The second property is that the deformation is independent on the third variable. So if you want, you can actually define it as a function which is defined on the cross-section. That's what you want, because that's what dimension reduction is about. You want to reduce the dimension of the problem. It's not really surprising that you get that. Look here. I mean, h is going to 0, so the effect of the third variable should vanish in the limit. What is maybe more surprising, or the important part of this compactness result, is that y has a higher regularity. You start with W12, and you get W22. That's important, because in a minute we will see that bending effects are involved, so you need a second derivative. Okay, before I come to the gamma limit, let me just introduce another notation. I want to save some space. So the first and second partial derivative, I will denote them by nabla prime. Okay. So this is sort of technical. No, I mean, you can do Poincaré if you want. That's a possibility. But in the original work by Friedrich, James, and Müller, they did not assume this. They were just saying that the derivative converged somewhere. But I mean, you can do it by giving a control here, or you do a Poincaré or whatever. I just keep that here for later, because in the case of voids, it's not just technical, you really have to assume it. So I was assuming it here for simplicity, but you actually don't have to do it. You get it by Poincaré. Yeah. Okay. So the gamma limit looks like this. So it's an integral functional where you have a quadratic form, and here you have the second fundamental form related to y. So what is this quadratic form? Well, there is a linearization going on. Namely, you take the Hessian matrix at the identity. That's the quadratic form Q3. And then you sort of reduce that. You relax it to something which is defined just on 2D, on the plate. And it's done like this. But I don't explain this today because that's not the focus of my talk. But you kind of relax from 3D to 2D. Well, what do you plug in? You plug in something which sees the curvature of the plate. And the way you do that is, well, you take the second fundamental form. So the second fundamental form, if you want, captures the derivative, the deviation of the normal vector with respect to V1 and V2. And V1, V2 are spanning the tangent space of your plate. Okay, so in this sense, you see that this is really an energy which sees curvature effects. So the last thing that I wanted to mention here is the ansatz for the recovery sequence. First of all, because I will need it later at some point. The second thing is that, as you know, it's always good to see the ansatz of the recovery sequence because it tells you something on what gamma convergence is doing. And here you see that the cross-section, so the midline, is an isometry. So you know that the gradient of this guy is always a rotation. And then if you deviate up and down from the midplane, you have a linear term here, which also takes the normal vector into account. And then there's a higher order correction, which is related to the definition of Q2. But the two first terms are the most important one. In particular, for later, we will need that the midplane stays an isometry. Okay, so now let me bring voids back to the story. So the two first terms, we have seen them already. That's the elastic energy, that's the surface energy. 1 over h, if you remember, that's the rescaling which was just coming from the volume. And here I'm keeping also the prefactor 1 over h squared, which is again telling me I'm looking to the Kirchhoff bending regime. Now, for technical reasons, I do a certain penalization, and I will comment on this a little bit more later, in terms of a curvature effect. So you have a prefactor here, which is going very fast to 0, faster than h. And this term here captures the second fundamental form of the void. It's important to mention that this has nothing to do with the curvature of the plate. It's related to the curvature of the void. So remember, you have a void, the void has a boundary, and here what enters the energy is the curvature of the void. Later in my talk, I will tell you why we need this. So if you want, for the moment, you can just ignore this. It's just it's going to be important later. So also here you need to, first of all, go to a fixed Fick domain. For the deformation, we have already seen this. I need to do the same thing for the void. So E is my notation for the thin void. My notation for the thick void is that it's V, and you see it's just done in terms of a rescaling. Here you also need to rescale the energy, but that's not important. The only thing that we will need in the following is that E is the void in the thin domain, V is the void in the thick domain. And then the first step is again that you have a compactness result. And here now, this is really important that I have it here. So in the elastic case, it was not important, but here I really want that. In the limit, you get a set of finite perimeter, the void set, which is a subset of the two-dimensional cross-section. And you get a limiting deformation, which is in this funny space, which I will explain in a minute. But let me first tell you what kind of convergence do you get. Well, you get convergence in the measure sense of the void set, and you get convergence of the deformations basically in the way we had it before. So you get strong convergence of the functions and strong convergence also of the gradients. Well, now what's this space here? SPV2 to isometry. So, well, it's the space where the functions are in SPV. The absolutely continuous part of the function is again in SPV, and you keep this isometry constraint that we have already seen in the elastic case. Let me phrase this a little bit more sloppy to hopefully get you an idea what this space is doing. So it's a space where you have a first derivative, you have a second derivative, and you have jump sets. You have jump set of the function itself, but you also have a jump set of the derivative. That's my notation for this. And you again keep this isometry constraint. So now we can go to the gamma limit. That's the main result. The gamma limit looks like this. There's an elastic part. That's exactly as in the elastic case of Friedrich, James, and Müller. Then there are two parts of the surface, and we have seen them at the beginning of my talk. So the first one is related to the voids. So remember, you can have a void here, and this void is deformed, and in the dimension reduction limit, this void can still exist, and you see it in the energy here. The second possibility is that a void collapses to a crack in the limit. You see it here, and in the dimension reduction, you see a discontinuity of the function. This is exactly as we have seen it already in the 3D model I was presenting at the beginning. But now there's something more here. There's something related to the jump set of the gradient. This is something that I don't have in the picture, but I will show you like this. So it can be that due to the void, you are broken somehow, but your function is not discontinuous, but just the gradient is discontinuous. So that's related to a kink in the material. And the kink in the material is exactly the term that you see here. It's important to remember kinks were not allowed in the purely elastic case, because in the purely elastic case, the function was W22, so kinks were not allowed. So really kinks is an effect of this model here. And that's the reason why Santilli and Schmidt called this a Blake-Sisserman-Kirchhoff model. Blake-Sisserman is exactly the term for a free discontinuity problem where you have presence of the jump of the gradient. And Kirchhoff, I mean, we were talking about this before. This name is coming from the elastic part of the energy, which takes into account the curvature effects. Now, speaking about Santilli and Schmidt, I mean, they proved the same, let's say they derived the same gamma limit, but under different assumptions. So now it's time to tell you what are the different assumptions, what were their assumptions, what did we assume. So that's my next slide. So in their paper, there was an important assumption, which is called the droplet assumption, minimal droplet assumption, which tells you something what happens if you take a little bit of a neighborhood of the void. So it's hard to understand that condition, so let me tell you more like a consequence of that. The consequence of their assumption is that they have a bound on the curvature of the void, and this is an L-infinity bound, and it's bounded by 1 over h. So in order to understand what it actually means, let's go to an example. Let's assume that all my voids that I have are perfect spheres. That's already enough to have the main idea in mind what can happen to voids. So in their case, they can have spheres, but due to this bound on the curvature, all the spheres need to have a diameter of h. And well, then they also have a certain upper bound for the number, which scales like 1 over h. So in this sense, they consider voids which are macroscopic because the height of a void is as high, I mean, in order as the material. So they cannot have inclusions which are smaller and smaller compared to the height of the material. For us, it's different. So again, thinking of spheres, with our curvature penalization that I was telling you before, each spherical void gives the same contribution. So we can have a higher number of voids. And the most important point is that we have no restriction on the diameter. So they can be as small as you want and can accumulate on different scales inside of the thin plate. Okay, and I will come to this point a little bit later again. So this is an important discussion in my talk to understand how this size of the voids sort of affects the problem. Then there's a second thing. This is more related to the limb soup. So Santilli and Schmidt, they just proved the recovery sequence under this regularity assumption that I was telling you at the beginning, which is related to the Minkowski content. And we actually showed that you can remove this restriction, so you can prove recovery sequence for all possible deformations. All right, so before I go to the proof, I wanted to briefly show you a related model, which is a three-dimensional rod. So you long in one direction and thin in two directions. And the model is basically the same, except for the fact that you need to rescale differently. 1 over h square is now the prefactor, which takes into account correctly the volume. Here you can also go to a limit. You have an elastic part, you have surface parts, which is now actually a little bit easier because in the one-dimensional setting, voids are just intervals and jumps are just points. So it's actually a little bit easier and you can derive a similar result. I'm not detailing this much. I wanted to show this for two reasons. Well, the first one is just to tell you, I mean, it's flexible enough to do that. And the second and more important one is when I will talk about the proofs in a minute, I will sort of take the setup of the rods because it's just a little bit simpler to explain the ideas for rods than for plates. Okay. So before we start, let me come back to this slide where I was presenting the difference, just to recap that in the case of in the case of rods, because it's a bit easier to understand. In the Santilli-Schmidt paper, basically they have spherical voids of diameter h, and they have a finite number in the setting of rods, and we can have a number which diverges as h goes to infinity. Okay, so here you see the main difference of the two papers. In particular, our voids can be as small as you want. All right, so this is everything that I wanted to show you on our results. Now, the second part of my talk would be about the proof ideas. And I want to proceed step by step as I did it with the results. I will first of all tell you what was the main idea in the Friedrich, James and Müller approach, and then I will progressively come to the ingredients in the void setting. Okay. And as I said, I do it for the rods because it's just easier to explain, hopefully. So I have a thin, long rod of length L, and the main idea of Friedrich, James, and Müller is, well, let's partition this into cubes of side length h. And then they take each of these cubes and they do their celebrated rigidity estimate. So they approximate the deformation in the thin domain by a rotation on each of these cubes. And they can control this in terms of the distance square of the set of rotations, which is basically related to our elastic energy. It's proportional to our elastic energy. Well, that's called a rigidity estimate. So why so? Well, imagine for a moment that the deformation gradient was always a rotation. That's the case that there is no elastic contribution at all. So the right-hand side is 0. Then also the left-hand side is 0, which means that the gradient is constantly a rotation, and therefore the deformation is a rigid motion. So that's where it comes from the classical Liouville result, and this is a quantitative generalization in terms of L2 norms. Okay, that's the main ingredient, and what the next thing that they do a similar argument to estimate the difference of the rotations on adjacent cubes, again in terms of the elastic energy. And then just to make things a little bit smoother, I will introduce a field which is close to each of the rotations in the respective cubes, but is a smooth function. So I interpolate between the different rotations, and then I divide both sides by h to the power 2. Then on the right-hand side, you just see here the elastic energy rescaled, and you have an energy bound on this. Okay, and on the left-hand side, I see a different quotient if I divide that by h, and if you want, this is very, very close to a gradient. So you see that actually what you control is the gradient of this field, which takes into account the difference of the rotations. And then you can pass to the limit here by compactness. And then the last step is remember that R or RH was approximating the gradient of Y, so the deformation gradient. Since R has a higher regularity, namely you have one derivative, for the deformation you get a second derivative. And you get that in the case of rods or also in the case of plates. So the higher regularity of this rotation field induces the second derivative for the deformation, and that's the key point in the compactness estimate of Friedrich, James, and Müller. Okay. So what do you do if you have voids? Well, the first case, the first who considered this problem were Santilli and Schmidt, and they were saying the following. Well, let's call a cube ugly if it contains a bit of void, because I don't know what to do. And in their setting, well, they do not have too many components of the void set. I told you before there's a bounded number of components. So there's only a bounded number of ugly cubes. And these you kind of throw away. You don't do anything with them. But on the complement, that are the sequences of the white cubes, everything is as good as in the Friedrich, James, Müller setting. So you can actually redo the argument there. This is only half of the story. I mean, they have to work a lot still to get the right energy in the limit. And let me just give you one idea that they have. So, and that's a clever idea that they're not actually considering the cubes of size h, but they go to a smaller scaling by looking to cubes of size h over n. And if they do this, then they see that the number of ugly cubes basically scales like the surface energy up to a lower order term, which goes to 0 if n goes to infinity. So I think this is a little bit too technical already, but the take-home message of this slide is that they identify the cubes where void is occurring, and then they try to redo everything on the complement of these ugly cubes. Okay, so what about our setting? Well, if you remember, we could have a larger number of voids and they could be smaller. So if I would like to redo this argument, then maybe all my cubes are ugly. Who tells me that it's not just scattered around and all the cubes are ugly? So I need to do a different argument. And kind of the key of the whole business is that you have a suitable rigidity estimate. So you need to come up with a more general rigidity estimate, which allows for the fact that maybe you have some void inside of your cube. And you don't need to assume that the cube is entirely empty of void. Okay, that's maybe the idea that you have, but then you realize if you have void inside your cube, the issue of rigidity is not such an easy business. And remember, what we saw before already is that by the void, it could be that the material is disconnected into two pieces, and then, well, I mean, maybe this is flying around and is rotated. So you already see any kind of rigidity you might hope for should be one which takes into account the different components differently. Still, I mean, well, here, another example on the right-hand side, the material is still connected, so the void is not disconnecting the material, but still, since this is a very small set, you could pull it a little bit, then you can squeeze it, you can rotate it without paying a lot of elastic energy because this is only a very thin tunnel. So the second problem is that you might have thin tunnels which can lead to a non-rigidity even if the set is still connected. So now the main idea that we had was the following. We passed to a thickened void. And we do that by taking a gamma neighborhood of the original void, and I call this the thickened void E gamma. And now I'm considering the connected components of omega without the thickened void. And this will ensure that there are no thin tunnels in each of the components. So such a thin tunnel will not exist in this component anymore, because by thickening it, if it was smaller than gamma, I would disconnect the two components. So this will ensure me that in all the components, the thin tunnels have a least thickness. And once I have a least thickness of the domain, then I can sort of control the rigidity constant. So that's the main idea. But this comes with a catch. I'm going to this thickened void set, and this increases the volume and the surface of the void. And this is something I don't want. Not too bad, at least. I would like that the volume is almost the same and I don't really change the energy by doing this construction. And why is this now dangerous? Well, you could have a lot of small components which are scattered, and if you thicken them by a fixed constant gamma, who tells you that these two properties still are satisfied? I mean, think that the void is really scattered a lot, and if you thicken it, maybe you get back the entire domain. So who tells you that something like this cannot happen? So we need to avoid this, and a way to avoid that is exactly this curvature penalization, which tells us that things like this, they can appear somewhat, but not in such a bad way. Okay, so a little bit more precisely, the result would go like this. So delta squared is my notation now for the elastic energy. F surf is taking into account the surface part of the energy with the perimeter part and curvature regularization. So the result roughly goes like this. So you start with your original voids, you thicken them without changing too much volume and surface. And then you get rigidity on each of the connected components Pj of omega without the thickened void. And here you see the Friedrich-James-Müller-like estimate. So I brought the rotation on the left-hand side, but this doesn't matter. And here you see this gamma in the denominator takes into account the thinness of the tunnels that I was saying before. The constant kind of is bad because you allow for thin tunnels. And I mean, you calculate that to the power 3. And then we have a second estimate, which comes from a linearization. And this estimate, even if you cannot really see this, is a little bit better. And so the main idea behind this is the following estimate, namely the symmetric part of F minus the identity can be controlled by the distance from the rotations. So this you control by energy if you want, if you square it. And then you have a higher order contribution of the full gradient. So, and this extra exponent helps you in order to improve the estimate of the symmetric part. You don't really see that because, I mean, the constants that are flying around here are too complicated. But let me go to the application in our setting. And if you do that, then you see here for the symmetric part, you exactly get h to the power 2, which was the Kirchhoff bending scaling, exactly what you want. And for the full gradient, it's a little bit worse. And the fact that this is a little bit worse is fatal. So in order to do this business of Friedrich James Müller by comparing the rotations on adjacent cubes, you need the exponent 2 here. And if you have something less, then you are lost. So you see, we have sort of a rigidity estimate, but it has two defects. Namely, you get a good estimate only for the symmetric part. And the second thing is I only get it for components. And if you remember before, I wanted to compare rotations on adjacent cubes. But which rotation should I take now? Should I take the one to P1 or P2, P3? What should I do? So there are two issues here that I need to sort of solve. Then the fact that I have components and the fact that I have a good estimate only on the symmetric part. Yes. Yeah. 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 Yeah, that's a good point. So the point is that I can still use the energy or the fact that I'm Sobolev on the original set. So in some sense, so what you're saying, so if maybe I have a thin tunnel, which is not so bad, maybe if I'm now doing the thickening, I make my life worse because I'm producing a thin tunnel, but I still can take the estimates on the original set. And this is also what I have to do. So producing new thin tunnels is not a problem because in the original set, they were not thin tunnels. Yeah, good point. All right, so on the next two slides, I would like to try to explain you how you solve these two issues. The issue with the components and the issue with the fact that you just have a control on the symmetric part. And the first one is our wish to understand under which circumstances you can be sure that you have one big component and maybe some small components. And if you have one big component, you take exactly this component in order to do the estimate of different rotations on adjacent cubes. And this is related to kind of a relative isoperimetric inequality. And we do that not on cubes, but on long cuboids, which have the cross-section of a unit square in the third direction, and which are long in the first direction. And the idea is that you get a relative isoperimetric inequality in the usual sense, but there is something which is good, namely if the surface of the void is so small that you cannot cut through once through the rod, then you can show that this constant is actually not depending on L. So usually in a relative isoperimetric inequality, the constant, of course, depends on the domain. But what we can show here, if you cannot cut through, then the constant is actually independent on the length. And this allows us to show that in this setting, you just have one big component. And by this, I mean that so if you denote the connected components by Cj, and C1 is the biggest set in volume, then all the other sets, if you sum their volume, you have this control in terms of the isoperimetric inequality. So this is the picture you should have in mind here on the left. So there is one big component, and then there may be small components flying around. There's a variant of this. The variant goes like this. So if you can cut through the material once, but not twice, then it can happen that you have the picture like this. So you have the void on the left and one component on the right. But you cannot have the picture on the right that you cut through twice and you have two big components. So also in this setting, you can sort of get that there is just one big component. Okay, so it's a little bit hard to digest for the moment, but my point is I want to have a characterization of cases where you can expect to have one big component. And in our setting now, I call this cube or the cuboid ugly if I cannot be sure that I have one big component. And the two cases are the following, namely, I cut through the material once, and the situation is like this, or the void is small and I cut through the material twice, which produces two components. And for later, these two cases are sort of tailor-made for my surface energy. This case here will produce a void in the limit, and this case here will produce a jump in the limit. Okay, so that's the first ingredient which should tell us under which condition I can get one component with a corresponding rotation, which I will use when I do the Friedrich-James-Müller argument. Now, the second issue was the fact that I'm actually just controlling the symmetric part of the gradient. What do I do here? Well, I mean, you could just say now, well, why do you really care? I mean, there's Corn's inequality. Do Corn's inequality. The symmetric part is enough to control the full gradient. And that's sort of what you do, but with a little catch. Namely, due to the presence of these little voids, Corn's inequality is maybe wrong in a certain sense, but it's true in another sense. And this other sense where you can make sense of Corn's inequality is that you cut out little balls where something bad happens. And these cut out balls, I call them little omega. And you get Corn's inequality as you expected. So you control the full gradient up to a skew-symmetric matrix in terms of the symmetric gradient outside of this bad set. And this bad set can be controlled in surface and in volume. And actually what's behind this construction, what you do, you try to find a Sobolev approximation, which allows you to replace u by a Sobolev function, v, on the entire cube, which coincides with u outside of this bad set. And then you do classical Corn's inequality. You just realize that it doesn't hold in these little cubes, in these little balls. And we adapted this result for our setting with voids, but this was done basically before for in the setting of SPD functions. And for instance, there are a couple of results in that direction. And for instance, Matteo and Flaviana have worked a lot in that direction. Okay, why is it good for me? Well, it tells me I can lift my problem from the symmetric gradient to the full gradient in case that the void set here or this exceptional set is small. And I do this by assuming that I only have a little void, say 1 over 100. If I knew that the void set is so small, then little w is also small, and I basically have a good control in terms of Corn's inequality. Okay, so now I call a cube good if it only contains a little void. And now I can wrap up. So that's my last slide on the lim-inf setting. Well, good cubes were those where I can do Corn's inequality. Ugly cubes are those where I am not getting a one fixed component, but I have a lot of surface energy. And then the third is that you have bad cubes that are sort of one which are in between, and that are the most delicate one to treat. So what do you do in the three cases? Well, for the ugly cubes, the surface contribution is so big that they will correspond to what happens in the limit for the surface part. So this estimate here will go to the voids. This estimate here with the prefactor 2 will go to the jump part. For the good ones, everything is set up in a nice way that you can redo the Friedrich-James-Müller business on the connected components. And then the most delicate one are the bad cubes or bad cuboids. And the reason for this is that, well, the estimate in the elastic case or the elastic estimate is not good enough to do Friedrich-James-Müller. But at the same time, the surface estimate or the surface bounds are not good enough that they would give me the right constants here for the surface energy. And well, that's the technical, the most technical part here now is to show that actually this is still enough to show that in the limit these cubes will not contribute either to the jump and to the boundary of the voids. This means, I mean, you don't get the right constants here in front, but you don't care because these cubes will not produce any voids or boundary of the void or jumps anyway in the limit. Okay, so let me tell you briefly something also about on the second case on the lim sup estimate without going much into details. So as I told you before, Santilli and Schmidt, they already proved the recovery sequence under this assumption. So the only thing that we needed to do is to get rid of this assumption, which is done by a density argument. Okay, so you do your, I mean, the naive idea would be do your favorite density argument in SPV. It's a bit, you know, different in my setting because I have a second order problem. So I do that for the function and the derivative, but that's not a big deal. I get regular jump sets, and once the jump sets are regular by density, I have the property with the Minkowski content. But where's the catch? The catch is the ansatz for the recovery sequence, if you remember that. The important thing was that the midplane was an isometry. Who tells you, if you do this approximation, that the gradient is still an isometry? Probably it's not. I mean, it's delta close if you want, but then you divide that by h squared in the energy and you're sort of lost. So this classical way of doing density arguments in SPV doesn't work. So we needed to come up with a density result which takes care somewhat of this isometry constraint. And it does it in the following way, namely it tells you that you're almost an isometry up to a small set. So there might be a small set where something bad happens, but in most part of the domain, you are very close to an isometry. So the function and the derivative are very close in terms of h to your original function, which allows you to repeat up to a negligible error term, the original ansatz for the recovery sequence. Okay, so this is probably the most technical part of the paper, I would say. So I think we all want to have coffee. So I just show you the picture. So it's done by a covering argument. And what you do a sort of a Whitney covering argument where you start with cubes on a certain length scale. And then inside you sort of refine that to get smaller and smaller cubes. And then you kind of wipe out the jump set in these smaller cubes. But I don't give you the details now, but I would be happy to explain over coffee if someone is interested, and I rather come to my quick summary. So the idea of my talk today was to present you a model about elasticity with voids. And the first thing that we did, which was an old story, was to see the relaxation result, namely that in the relaxed formulation, you see also discontinuity. So it's a free discontinuity problem. And then I presented dimension reduction results from basically or mainly from 3D to 2D. And I was comparing this to previous results in the literature. So the three main ingredients to my view of that work are the following. So we have sort of a rigidity estimate, which takes into account voids, and this is necessarily in the sense of component rigidity. Then to identify big components, there was a relative isoperimetric inequality. And the third thing, which I was not explaining too much in detail now, was the density result, which takes care of the isometry constraint. Okay, that's it. Thanks.
Thank you, Manuel. Questions?
Yeah, thanks, Manuel. A very nice talk. And this is also a very nice result. And you kind of made clear that it's kind of, I think I understood correctly, it's hopeless if you don't make any further regularization assumption that you made. And it's much weaker than the Santilli-Schmidt assumption. I'm just wondering, so I mean, if you do kind of these higher order regularizations, if you do this on the whole space, it doesn't matter if you take the second derivatives or the Laplacian. And here in some sense, you take the second derivative, so kind of the full curvature tensor. What about the trace, the mean curvature? Would that be enough? Because I mean, I think there was one point where you needed the volume growth or the area growth. And that is kind of exactly what this would capture. So is the mean curvature enough, mean curvature squared?
Yeah, so we thought about this a little bit, and I think a main ingredient of the proof is the almost graphical representation result by Simon. And this takes the second fundamental form. You can replace it by the mean curvature, but then I think you need some assumptions on the topology. So you need to really assume that they are spheres. But if you do something like this, then everything goes through. I mean, you need some topological assumptions, but then you can replace the second fundamental form by mean curvature.
Yeah, but I mean, without the assumption, kind of just in the energy, it's not clear that you can do this. Okay.
I mean, that was going to be my question. I mean, you made this distinction in your pictures between, you know, you have parts flying off, you have small necks, and then you said you need that curvature assumption basically to argue away these small inconsequential inclusions. Could you imagine a construction where you know, at the level of the cube, you distinguish these cases and thereby remove potentially the curvature assumption?
So it's where, I mean, we thought a lot about this. We were not able to do it. So of course, I mean, I can just say there are two issues. I mean, there are these very small components. If you thicken them by a fixed constant, that's very bad. So you need to kind of be sure they're not there or not too many. And the next thing is that maybe you have a big component, but this has like of tentacles coming out in a very strange way. So you could have a big component, but then you have like these tentacles coming out, which is a second source of difficulty. That's all that I can say. I mean, I was trying to do this for a lot of time, and then kind of I had the idea that it should become simpler in adding the curvature regularization, but without, I just don't know.
But you had Korn's inequality without this issue, right?
Yeah, but Korn's inequality. Yeah, Korn's inequality. That's we know much more about Korn's inequality because it's a linear estimate, and that makes everything much simpler because the proofs that we have for Korn's inequality, they're based on slicing or on convolution mainly, and this is something that you cannot do in the nonlinear setting. So so what helped us a lot is something like this. You first of all do a bad estimate sort of for the nonlinear rigidity estimate. Then you kind of improve the scaling, and then you can do a Korn's inequality. That's
okay. Because somehow geometric rigidity, Korn's inequality is somehow the linearized version.
Yeah.
So,
but it's easier because it's linear.
Yeah, sure.
Yeah.
But okay. Thank you.
Other questions? So did you try to play a bit with the boundary loads to, to have understand something on the minimizers?
No, we did not. I mean, I was showing at the beginning the boundary conditions just for motivation, but we just did the plain gamma convergence result.
Okay, well, thank you. If there are no further questions, we thank Manuel.
Okay.
So maybe it's time to start for the last talk. So it's my pleasure to introduce Flaviana Iurlano from Genova, and she will talk about the lower semi-continuity, relaxation, and phase field approximation for superlinear models.
Okay. Thank you very much, Roberta. Thank you, Roberta, Alice, Giovanni, and Matteo for this invitation. I'm very happy to be here today. I will present a joint work together with Sergio Conti and Matteo Focardi concerning some fine properties of a particular type of energies, which are called in this talk superlinear energies. I will explain in a few minutes what does I mean for superlinear models. So the context is that of variational models involving free discontinuity problems. So let me write exactly what kind of energy I have in mind. So I consider an energy of type integral of omega of psi of some gradient of u plus integral on ju of some g amplitude of u nu u dh n minus 1, where here I consider omega a subset of Rn, the reference configuration. It's an open-bounded Lipschitz set. U is, in this formulation, U is already a function, a special function of bounded variation from omega with values in Rm with the usual notation, so amplitude of the jump, normal to the jump set of u, and absolutely continuous part of the gradient of u. The space is the space of spatial function of bounded variation because, as we will see, this is the right space where setting this type of problems. We are interested into studying minimum problems involving this energy. So, for example, we can think about a problem in which we have to minimize this energy under some boundary condition or under some additional term involving loading. The main point, of course, the main feature of the model is related to the choice of the two densities, so the density of the bulk part and the density of the surface part, psi and g. So the choice depends on the model we are considering. In general, psi is a function with some regularity, in particular with Q growth, with some Q greater than 1, and G is, again, a function with some regularity. I will be more precise later, which satisfies one of these two properties. Either G is of this type, so either G is such that Gz nu is greater than C for every Z and nu, so for every Z in Rm and nu in S n minus 1 for some constant G, or G is 0 in 0, is 0 in 0 with some particular behavior in 0, so such that the limit as Z tends to 0 of G Z nu over Z is in between 0 and plus infinity included. So the first choice for G corresponds to a case in which we have a control from below of the density. So, for example, this is the case of the Manfred-Shaw energy, where, for example, G identically equal to C gives an energy in which here we have just the length of the jump set. The second choice, which is our choice, that will be our choice in this seminar, is the case in which G may be 0, and in particular it is 0 in 0 when the amplitude is 0, with some behavior that can be of linear type if this limit is finite and non-zero, or superlinear type when this limit is plus infinity. So if this limit is L, I say in 0 plus infinity, we will talk about linear behavior for G. And this is the case, for example, of the variation, when we have, for example, the norm of Z, G equal to the norm of Z. The second case is the case in which this is exactly equal to plus infinity. In this case, we say that G has a superlinear behavior, and an example can be given by the square root of the norm of Z, for example. So in this talk, I'm interested into superlinear models in the sense that our bulk energies will be superlinear, so with Q growth and Q greater than 1. So superlinearity here is in plus infinity, so for very large gradients. And we also require superlinearity for the surface energy, but in the origin. So superlinearity for the surface energies means that we are requiring that G is superlinear close to the origin. Okay, so the prototype model is the square root of the norm of Z. So in general, the prototype of our energy is the gradient of U squared plus the integral of the amplitude of U. Okay, this is the simplest one, of course. We will consider more general models. What is the difficulty in working with this type of energy, with the superlinear energies? The difficulty is that if, let me call this energy E of U, the difficulty is that if we have a function U, if we have U such that the energy is finite, the finiteness of the energy doesn't imply that the length of the jump set is finite. And also, if we have a sequence of functions for which the energy is equibounded, equiboundedness of the energy doesn't imply equiboundedness of the length of the jump set. And this complicates a lot calculations and make all arguments more technical and more difficult. We will see. We will see in some cases what happens. Okay, these kind of energies appear in many physical models, in many applications. For example, in asymmetric thin films, in screw dislocations, in single crystal plasticity, in polycrystals, but also in some models in fracture mechanics and in imaging. Anyway, we are interested into three variational properties, and in particular we are interested to comment, to discuss these three aspects. The first question concerns the direct method of the calculus of variation for E. This means okay, we have this energy. Our aim is to discuss the existence of solution of minima for minimum problems involving this energy with some boundary conditions or additional loading terms. Can we apply the direct method? So what can we say concerning compactness and lower semi-continuity? And okay, I will discuss more precisely later, but in particular, I will focus on our contribution, which is in particular lower semi-continuity, for anisotropic surface energies. There are some partial results concerning compactness and lower semi-continuity. I will discuss them later. Second question. Okay, suppose to have answered to the first question, so to have identified the right properties to ask to psi and G in order to ensure that E is lower semi-continuous and compact. Now the question is, suppose not to have this hypothesis, and you want anyway to solve a minimum problem connected with this energy. So of course we have to relax. We have to relax. So the second question is how relaxation does it work? So if psi and g don't satisfy the properties identified in Q1, what can we say if we relax our function? So what kind of envelopes we find in the relaxations? And the third question is the phase field approximation. This means for many applications, it is convenient to pass from sharp discontinuities to diffuse discontinuities in the spirit of Ambrosio and Tortorelli for the Manfort-Shah. And so here what I mean for phase field approximation is exactly to provide a sequence of phase field functionals gamma converging to an energy which satisfy the properties identified in Q1, in fact. So satisfying for psi and g the right properties that give lower semi-continuity and compactness. No, if this limit is 0, when one relaxes, we get 0. So it relaxes to 0. Yes. If it is finite and non-zero, so it is L, this means that it behaves as a variation. Our functional is more or less a variation. And so the right space is not SBV, but is BV. So in fact, but this must be finite. So in the linear case, when we relax, even if here we have quadratic behavior, Q behavior, if this is linear, when we relax, we get the linear behavior. And the right space is BV and not SBV. Okay, so let's start with the first question. So, lower semi-continuity. As I said, lower semi-continuity and compactness. So, as I said, there are partial results on this question, on this part. And so I don't have so much time, so I try to sketch what are the known results. So compactness and lower semi-continuity for isotropic psi and g. This means psi, which depends only on the norm of psi, and g, which depends only on the norm of z. So compactness and lower semi-continuity in the isotropic case, so under this assumption, is okay. This is, in fact, is classical. This is contained, for example, in the Ambrosio, Fusco, and Pallara book. So we are interested under suitable hypothesis, of course, on psi and g. For example, the simplest hypotheses are psi convex and g concave, plus some continuity, some good regularity properties, and some, of course, growth, superlinear growth. We are assuming superlinear growth for psi and g. So in the isotropic case, everything works well. And in fact, for compactness is enough, because if we have growth, if we have a control from above, from below, for compactness, it's enough to consider the isotropic case. So we are interested now in lower semi-continuity for anisotropic functionals. And in particular, as I said, we are interested in the surface case, because for the bulk term, again, the result is known, is completely known. I will say something after the surface, after having discussed the surface part. So now let me introduce our result. which is lower semi-continuity for anisotropic surface energies. Okay, so let G be a continuous function from Rm times Sn minus 1 with values in 0 plus infinity, and satisfying the following properties. So G is BV elliptic, G satisfies a sort of compatibility condition in the sense that G minus Z minus nu is equal to G Z nu for every Z and nu. This is just to give a sense to the integral on G of G. I mean, if we change the orientation, the integral must have sense. So if we change orientation, the amplitude must change sign. The third condition is a growth condition on G. So we don't ask to G to be isotropic, but we ask that G is controlled from above and below by an isotropic function. So we have something like 1 over C G0 of Z less than G Z nu less than C G0 Z. I will say in a minute what is G0. So for the moment, G0 is an isotropic function. For the fourth condition is a subadditivity, a sort of subadditivity condition on G, but G depends on two variables. So what does it mean, subadditivity for G? Is a subadditivity with respect to this G0. So we ask that G of Z nu minus G of Z prime nu is less than a constant times G0 Z minus Z prime. So these four properties up to now are quite standard, quite natural. I mean, they are some generalization, natural generalization of the conditions we find in the isotropic case, for example. And 5, we have to add another condition. This is much more restrictive. So let me write it before. Limit as Z S, we call it S, going to 0 of G0 S over S to the power gamma is in between 0 and plus infinity for some gamma in 0, 1. Okay, this is more restrictive because here we are assuming not only that G0 is superlinear, but we are assuming that G0 has a power law growth in the origin. So it is a power S to the power gamma with gamma in 0, 1. This is quite restrictive, but as I will show, it seems to be crucial for the kind of computation we perform. Of course, the fact of assuming this condition prevents us to treat a class of models, which are the models, for example, in which G0 behaves as T log T. So, of course, this kind of model is not included in this condition. And unfortunately, this appears in applications, but okay, we are not able to cover it. If G0 is isotropic with this behavior, anyway, one can use classical results and one is able to treat anyway this case. Okay, so let me write what is the conclusion. So let Uj be a sequence in GSBV Okay, here we consider GSBV in place of SBV, just because our functions G may be bounded. So we don't have a priori control on the variation, on the entire variation of Uj. But if one wants, one can restate the theorem in SBV. So it's the same under some suitable additional conditions. Okay, so let Uj in GSBV such that Uj converts to some U in GSBV in measure. And we also assume that the sequence of the gradients of Uj is equi-integrable in L1. Here we have to add a condition of this type because we are not assuming any control on the bulk part for this theorem. When we will consider complete functionals involving a bulk term and a surface term, it will be enough to assume for psi a Q growth with Q strictly greater than 1 in order to get equi-integrability in L1. Anyway, here we assume this because we are not involving any psi in this statement. Then we have the lower semi-continuity inequality, that is the integral of G U no U is less than the lim inf of J Uj G Uj no Uj. Okay, I will give an idea of the proof of this result, but before this, let me say something more concerning partial results on this part, so on lower semi-continuity for anisotropic surface energies. The partial results are of the 90. The first is Ambrosio and Brides in the 90, and this is in the context of minimal partitions. So in fact, Uj is in this context, Uj takes values in a finite set. And the second one is Ambrosio of the 90, in which Uj is not forced to take value in a finite set, but there is an hypothesis on the control on the jump set, on the length of the jump set of Uj. That in our context, as I said, is not so natural because G is not bounded from below, G is 0 in 0. So assuming a condition of this type doesn't come from the model. This is not a compactness assumption that comes from the boundness of our energy. Okay. So let me give a sketch of the proof. Okay, the general strategy of the proof is not so different from the proof by Ambrosio, assuming the uniform bound on the length of the jump set. And the idea is essentially to use BV ellipticity to get this inequality. So maybe I recall what is BV ellipticity. G is BV elliptic if and only if the G Z nu is less than the integral of G U nu in a cube with one side orthogonal to nu. This for every U, which is piecewise constant. This means piecewise constant on a Cacciopoli partition of the domain. and satisfying a boundary condition. This means that the support of u different from the characteristic function of, we say, jump u in x0 times no, I write different from the function which is u plus x0, u minus x0. This way is maybe more clear. When x scalar nu is positive, x scalar nu is negative. This has to be compactly contained in Q. Okay, so U piecewise constant and satisfying some good boundary conditions. This is, sorry, this is Z and 0 in our context. So Z and 0. Okay, so the idea is to reduce to the hypothesis of BV ellipticity. So the idea is to reduce U to be a function taking just two values and uj to be piecewise constant with right boundary conditions in a way to reduce the proof of the limit inequality to just to definition of BV ellipticity. So the general strategy is exactly the one by Ambrosio, but we have a delicate point due to the fact that we don't have a control on the measure of the jump set. So the first point, the first step of the proof is precisely blow up to reduce, to pass from U to the function U plus x0, U minus x0 in the 2/2 of the cube. This is just blow up. Okay, so we can pass by a general function, from a general function to a function just taking two values in the 2/2 of the cubes. The second point, the second step, is is using coarea to pass from uj to piecewise constant to a piecewise constant sequence. Okay, this is more delicate, and in fact, this is the step which uses property 5. And the reason is that it is, okay, coarea, the use of coarea is standard. I mean, we apply coarea to each component of uj, and we just consider some suitable level sets in a way that the difference between the amplitude of the new sequence from the original sequence, so the difference between the amplitudes is small, is less than an error epsilon. So this is just a standard use of coarea. The problem is the estimation, and in particular is the estimate of the part where the jump set is very small. So is the estimate of the part where the jump set is very, very small. So let me say small than some eta epsilon, where epsilon is the, as I said, is more or less the difference between uj, let me call uj tilde the new sequence, uj tilde minus uj. So this is less than some constant times epsilon. In fact, this is just a 2 epsilon. And here we want to estimate the energy in the set where this amplitude is very small, so smaller than some eta epsilon, with epsilon smaller than epsilon. This is exactly the part, the energy, which cannot be estimated by this condition. Okay, it's the part where the amplitude is very, very small. It's very close to 0, but it's not 0. And it turns out that after some computation, it turns out that this behaves, can be controlled at least by something which is of type G0 epsilon over epsilon times eta epsilon over G0 eta epsilon. Now, we want this term to be small, but this is not always small. I mean, if we assume a condition of that type, so a condition of type power law growth in the origin, this is small, this is infinitesimal, and this can be neglected. If G0 is T log T, this is not infinitesimal, so we cannot conclude this argument. Of course, in that case, probably this estimate is not optimal. Okay, anyway, this is the point, the only point, in fact, where we use that hypothesis. The only point in the entire talk where we use that hypothesis. Third point, third step, and the last step of the argument. The last step is in order to recover the BV ellipticity definition that I wrote here, we need a boundary condition. So we need the sequence uj bar, uj tilde to satisfy the right condition of the boundary. We don't have this right now. So we have to modify. So we modify u tilde j to get the correct boundary condition. The correct boundary condition is this one, okay? U plus x0, u minus x0. Then, finally, use definition of BV ellipticity. Okay, and this gives the lower semi-continuity inequality. This concludes more or less the proof of the lower semi-continuity result for surface energies. Let me say 2 words concerning lower semi-continuity for volumes. This part, in fact, is already known, so I will not discuss it in details. In fact, there are 2 results. There is one result by Ambrosio of the 94, again under a condition of that type, so under a condition on the measure of the jump set. And there is another result by Christensen, 99, which replaces this hypothesis with an hypothesis on a function of type G0, where G0 satisfies, maybe I didn't discuss G0, so now I add, but it satisfies very standard hypothesis. Anyway, Christensen requires, in place of a control on the length of the jump set, a control on G0 of the amplitude of uj, where G0 is superlinear, is just superlinear. Okay, so satisfies our hypothesis, but in place of 5, in place of the power law growth, is just superlinear. So the limit of G0 z over z goes to plus infinity. And here I have to add what is G0. Okay, here G0 is a continuous function non-decreasing, subadditive, which is G0 just in 0. So G0 minus 1 of 0 is the only point 0. So very standard hypothesis, very basic hypothesis on G. So continuous, monotonic, subadditive, and 0 just in 0. Okay, so let me pass to the second question. So relaxation. For the second and the third question, there are less results in the literature. And the reason is that the fact of considering isotropic functions, it doesn't help, in fact. The problem is constructing the recovery sequence. So recovery sequence starting from an ugly function. If psi and g are isotropic, this doesn't help in the construction. So the problem is that we need a density result that allows us to pass from a general SBV, GSBV function to something which is more regular, for example, piecewise affine. So Q2, relaxation. So let me state the theorem. Let psi be continuous and satisfying some growth conditions. So 1 over c times psi to the power q minus c, maximum with 0, less than psi, less than psi, less than psi q plus 1. Now q is strictly greater than 1. Christensen, okay. Here in Christensen, I haven't said that this is one of the hypotheses, but the other hypotheses are psi to be quasi-convex and with the q growth possibly with the q equal to 1. So q is greater or equal to 1. Here, q is strictly greater than 1. Okay, so let psi be continuous and satisfying some growth condition from above and below, and let G0 and G as above as in 2, 5. So we only remove the hypothesis of BV ellipticity. So we remove the hypothesis of quasi-convexity for psi and the hypothesis of BV ellipticity for G. Then, if we consider the functional h of u defined as the integral of psi plus g in this for u, which is the best possible choice for u, so piecewise affine from Rn to Rm. Piecewise affine on we can also take a finite decomposition, a locally finite decomposition in simplexes of Rn. Yes. But this is just for lower semi-continuity. In fact, no, yes, we have also an alternative proof of this result. In fact, the fact of requiring the growth with q strictly greater than 1 is just to get the equiintegrability of the gradients for the surface part. But for the volume part, it's just it's enough to consider q equal to 1. We also have an alternative proof. The original proof by Christensen is using the Young theory, the Young measure theory. We have a more direct proof based on Zhang approximation, Zhang truncation lemma and approximation of quasi-convex superlinear functions by quasi-convex linear ones. But q equal to 1 is allowed. We can discuss of this later, of course. Okay, so I consider this functional where U is piecewise affine and on a locally finite decomposition of the domain, and I take U that doesn't charge the boundary, so Hn minus 1 of the jump set of U intersection with the boundary of omega equal to 0, and plus infinity otherwise. Then we have that the L1 relaxation of H is the functional H0, which is given by the envelopes, the quasi-convex envelope of psi plus Ju, BV envelope of G, for U in GSBV M and L1 because we are considering the L1 relaxation. And here the envelopes, the quasi-convex envelope and the BV elliptic envelopes are defined in the usual way, considering the supremum of the quasi-convex functions and BV elliptic functions lower or equal than the given function. And then we can prove an alternative characterizations of these envelopes using giving a self formula. So also a characterization in which they can express through a self formula. But this will be more clear in a minute, I hope. As I say, the partial results concerning relaxation are not so many. There is a result by Buscité, Fonseca, Leoni, and Mascarenhas, but involving in Buscité, Fonseca, Leoni, and Mascarenhas, maybe, I don't remember the year, maybe 2004, I don't remember exactly, but under, again, Hn minus 1, Juj bounded. So, in fact, the proof of Buscité, Fonseca, Leoni, and Mascarenhas is in the case of functionals defined on SBV Q functionals that includes a condition of this type, so the finiteness of the jump set. Okay, so idea of the proof. The main idea, the main point of the proof is, as I said, is to prove the inequality. Okay, the most difficult part is to prove the inequality. Let me call this H bar and this H0. So the most difficult part is to prove this, that H0 is greater than H bar. And the difficulty here is to construct, in fact, a recovery sequence to reach exactly the quasi-convex envelope and the BV envelope. In order to do this, the first step is to use a density result, and this is, in fact, the main tool, the density result, the main tool that was not available at that time. Density result, which is contained in another paper together with Sergio and Matteo. It's anyway 25, but it is already published. Okay, I write in this way. The density result says that given U in GSBV M, with energy finite, let me say H0 finite, we can approximate it by a sequence of functions Uj, which are of the type PA, so piecewise affine on a locally finite decomposition of Rn in simplexes, strictly in energy. So there exists uj converging to u strictly in energy, so in L1 and in energy, so H0 uj going to H0 of u, with uj piecewise affine and not charging the boundary. So in this way, we can pass from U GSBV M to any function which is piecewise affine on a partition in simplexes then that jumps only on the union of the boundaries of these simplexes. So this is the main point. The rest of the construction is just an explicit construction starting from a function of that type. So let me sketch it. So the second point supposed to have a function of that type. So affine on a locally finite decomposition of the simplexes. So what we do is to separate the constructions for the bulk and the surface part, so for the interface. So inside each of these simplexes, here u, the gradient of u is constant. So in each of these, gradient of u is constant. And we can use the alternative characterization of the quasi-convex envelope of psi in order to find an optimal profile phi, which is also piecewise affine, optimal for, let me say, psi qc gradient of u. And then we have to, so this is the construction inside for the bulk part. Now, the construction for the surface part is a bit more involved because we do this on the interface, but we need, in order to develop this construction, we need to have two values constant on the two cubes. So we take we take here some cubes or of small side rho. And in each of these cubes, we replace u, which is affine on the two sides of the cube, by a new function, let me call it v, which is constant on the two sides of the cube, just taking the value in the middle point of the cube. And then we can use the alternative characterization of the BV elliptic envelope of G that is proved using again the density result, saying that there exists some V piecewise affine optimal for G BV of the amplitude of u in x0, let me say like this, nu, where x0 is the point, the middle point of the cube. And gluing together this construction gives an entire function, a function defined on the whole domain omega, which is piecewise affine and satisfies the good estimate for h. So this is in fact the end of the proof. For rho, which is small, of course, rho small. Okay, in the last 5 minutes, I would like to discuss the third question. In fact, I would like just to state a version of our non-optimal version, of course, of the phase field approximation. So let us consider psi as before, so psi continuous. For simplicity, let me take here q equal to 2, but it's just a simplification. So the result also for any q greater than 1, but with q equal to 2, the result will be more similar to the original Ambrosian Tortorelli result. So let psi be continuous, satisfying the growth conditions. So 1 over c psi squared minus c maximum with 0, less than psi, less than c psi squared plus 1. And we suppose also that psi infinity, which I will define it in a while, this is the two homogeneous recession function of psi infinity of psi is greater than psi infinity of psi nu tensor nu. We call it projection property for psi infinity. For every psi and nu. This is a sort of slicing property, but it's not precisely a slicing property. I mean, psi infinity doesn't need to be isotropic. If it satisfies this condition, it doesn't need to be isotropic anyway. Psi infinity, what is? Psi infinity of psi is defined as the limit as t tends to plus infinity of psi t psi over t squared. So it's the two homogeneous recession function of psi. And we assume that this is uniform on the set psi equal to 1. Okay, under this hypothesis on psi, we can define the sequence of phase field functionals as in Ambrosian Tortorelli. So f epsilon of uv defined as the integral of f epsilon v psi gradient of u plus 1 minus v squared over 4 epsilon plus epsilon gradient of v squared. Okay, so the modica mortola part is still there. The only change with respect to Ambrosian Tortorelli is the potential, is the function depending on v in front of the gradient of u, and this has a special form. F epsilon of t is defined as a truncation of the function t over 1 minus t to some power p times epsilon to the 1/2 with p strictly greater than 1. This will give the power law growth of the surface energy. Okay, under this assumption, we have that f epsilon gamma converges in L1 times L1 to a functional f where f of u, I define it just for v equal to 1, otherwise it is plus infinity. F u1 is the integral of the quasi-convex envelope of psi, gradient of u, plus integral of g u nu, where G is in fact implicit, is a surface energy which is implicitly given by our data. This is for all U in GSBV, GSBV M and L1 with gradient also in L2. And here, okay, I don't write explicitly the formula for G. G is given by SL formula. G given by SL formula. And I just say that G behaves as the norm of, let me say, T to the power 2 over T over P plus 1 as T tends to 0. Let me say Z as Z tends to 0. So it satisfies the power law growth. It turns out, since it is a gamma limit, it turns out to be BV elliptic and to satisfy all the properties I said. Okay, I'm finished. In fact, if this projection property is not satisfied, we have only partial results, so we don't have a full gamma limit result, but just a lower limit and an upper limit with different surface energies. But okay, I don't have time to discuss this, so thank you for your attention.
Flaviana, for the nice talk. Are there questions? Remarks? Yes?
Hi. Thanks for the talk. So if you start from the function G, is it not possible to design the phase field model which will give back the function that you started from?
Hey, this is a very good question. For this superlinear model, I think it's not known, but Matteo Focardi with Roberto Alessi and, sorry, Francesco, okay, sorry, just published the 2 papers concerning exactly this question in the 1D case for linear, both, also superlinear. Okay, so the question is yes, but in the 1D case.
But in the 1D case, you don't have anisotropy, no? Yeah, it was not.
Other questions? So this is vector valued.
Yeah.
Okay.
Yeah.
So, but so naive question. These growth conditions also for this distance square from the group of rotations. If you take no.
Yeah. In fact, yes. There are. In fact, I can show you an example of a function psi that satisfies that condition, which involves, in fact, the distance from the rotation. In fact, that is not isotropic, because if it is also isotropic, it's easier, of course. So let me think. If we take psi of psi equal to psi squared minus 2 positive part squared plus determinant of psi minus 1 squared. This is minimized over SO2, here M equal to N equal to 2. This is minimized on SO2, and in fact, one can check that the psi infinity satisfies the projection property.
Thank you. There are no other questions. We thank Flaviana again.
Okay, let's start. Welcome back to the afternoon section. The speaker is Michael Goldman, who will talk about curvature penalization of strongly anisotropic interface models and their phase field approximation.
So thank you very much, and thanks for the organizers for the invitation. It's always a huge pleasure for me to be here. It almost feels like home. I spent, I think, 3 periods of 6 months in Pisa, so for me it's always coming back. So actually, I think it's the first time I'm giving a talk on the Mumford-Shah. Last time I talked about Mumford-Shah was in here for the exam of Luigi Ambrosio. So I had to study the paper of Mumford and Shah. So it brings back also very old memories. Anyway, so what I want to talk about today is a joint work with Jean-Francois Babadjian, which is here, and Blanche Buet, both from Orsay. So for the most part of the talk will be about things that I think most of you know already very well, so about Mumford-Shah and Modica-Morton approximation. But since the model that we want to look at the end is quite involved, I thought it was better to go slowly, especially after lunch. And I think it's the 5th week of conference for people in Pisa, so probably they are happy not to have too much information. Okay, so the aim, so in general words, is to model fractures with a strong anisotropy. So we already saw some things about fractures with anisotropy in the talk of Flaviana, and I think also in talk of Manuel. But here I will be interested mostly in this word strong anisotropy. But before I talk about the anisotropic model, let me remind you the classical isotropic Mumford-Shah functional. So here I will look at d equals to 2. So I mean, d is for the dimension. So most of the talk will be for either R2 or R3. And for the fractures, I'm only interested in R2. But so, I mean, we already saw that before, but what is this Mumford-Shah functional? So say you have a body, which is called here omega. And it's fractured, so there is some set K here, which is, in my case, one-dimensional. And it can have also branch points and what's called a crack tip, so where the crack is ending. So, okay, the fracture, and it has crack tips and multiple junctions. And you have a deformation U, which is, so it's an elastic deformation, which is H1 outside of the crack. And so the energy that you want to minimize, let's call it MS of U and K. This is made of 2 parts, so I'm representing the simplest version. So you have the integral of omega minus K of grad U squared. And then you have a term which is penalizing the length of the fracture. So you have a plus H1 of K. So this model was initially introduced by Mumford-Shah for image segmentation, but I think nowadays it's only used in mechanics. For the image, it's not so relevant anymore, I think. Anyway. And so the problem is that it's not so clear how to prove existence of minimizers in the naive class. And so now a very classical way around is to see your function as a SBV function. And then you see K as being the jump set of U. Okay, so if you want your function is kind of nice and smooth outside of K and it's jumping on K, and so you can kind of identify these 2 sets. And now you have the anisotropic variant. So I have a phi, which goes from S, let's call it general, to R plus, let's say continuous. And now I want to replace this part here by an anisotropic version. So I look at the integral, let's now omega, grad u squared plus the integral on the jump set of u of phi of the normal, where I choose an arbitrary normal on the jump set. So I will always assume that phi is even, so it doesn't see the orientation. And here I have the H1. So what we saw from Flaviana's talk is that things work pretty well if phi is what she called BV elliptic. So in this case, it's quite simple what it means. I want that the one homogeneous extension of phi is convex. This is okay if let's say convex. But there are some materials where it's quite natural to look at phi which are non-convex. That's what people in the mechanics call strongly anisotropic materials. And you know that if you really just want to minimize this functional here for a strongly anisotropic function, then you will see the relaxation and you replace phi by phi star. Because you will naturally see very fine oscillations which will disappear in the limit. So the question is, how do you avoid this relaxation mechanism? So one quite natural idea is to penalize a higher order term like a curvature term. So write it here. So instead of that, I will add plus. I'll try to use the letter H every time, where H is the mean curvature of G. Okay, so this is a very natural idea and has been proposed many times for many related models. And now the question that we want to address first is it really helping? Like, do you restore lower semi-continuity of this functional? So this is actually quite delicate, but and then the other question is, can you approximate with a phase field model this energy here? So that's kind of what I want to describe today. So we were motivated by this question from a paper by Lee and Morini, which are two people in mechanics. And so one problem that you see directly on this picture is that if I see Ju, as a, sorry, set here, it's non-smooth both at the multiple junctions and at the crack tip. So, okay, if I associate, maybe. So one thing you can do is associate to Ju varifold. We can look at V, which is H1, so it's the measure, H1 restricted to Ju, tensor product with the Dirac mass at the tangent space at Ju. So if you see this set as a varifold, you see that it doesn't have a bound and mean curvature because of the crack tip and the multiple junctions. And so the question is, how do you give sense to this energy here? So one possibility, so I think I will use often this notation. So what I call mu v is just the spatial part of the measure, so it's just H1 restricted to Ju. And so if I look at the first variation of this, what I will see is that I have minus h mu, where this is the mean curvature in the classical sense, assuming that the set is smooth outside of the crack tips, plus sigma, where sigma is atomic measure. So sigma is sum over I of alpha I delta xi. And so the xi's are the multiple junctions and the crack tips. And here the alpha I, they come from the tangent vectors which are arriving to the multiple junctions. Okay. And so one way to incorporate these things in a good way in the functional is to look at the following things. So J of U, it's just like before. So this. And then you just pay 1 per element in sigma. So plus the cardinal of the support of sigma. Okay. And maybe notice that if I have 120-degree triple junction, so if I have something like that, then there delta V is equal to 0. So in this model, I am not counting the triple junctions as a singularity point. Okay. So actually, if you are just interested in the lower semi-continuity properties of this function, it's quite easy, or at least cheating a bit. So indeed, since you have only a finite number of curves because of the penalization of the number of, say, triple junctions, you have finitely many C1 1/2 curves. So and for which you are controlling the W22 norm. And so you can pass to the limit. So see, for instance, Breides and Mark. So in some sense, for the question of the lower semi-continuity, you don't even really need to introduce variables, etc. You could just do it by hand. And here, the even existence of minimizers for this model is relatively easy. So the question that you want to ask is, how can you construct a phase field approximation? And so for this, I will go kind of backwards. So we start with a much simpler case, which is the case of boundaries. So instead of looking at the case of cracks, now my unknown is a set E. And my energy, it's J of E, which is the integral on the boundary of phi of nu plus, and I will put a parameter delta here, h squared. And for this case, I'm looking both as d equals 2 or 3. And so basically, it's this problem here, where I assume that there are no crack tips and no triple junctions. You can kind of get back to the situation here. And actually, this model here has been studied a lot. So for instance, by Gourtin and Jabour. And then there's a more recent paper of Torabi and al. And there's a very nice paper by Breides and Malchiodi, which consider what's happening when delta goes to 0. Okay, so here, so now before talking about phase field approximation, let me go back to the question of lower semi-continuity. So what we could prove, so okay, maybe one comment before I state the result. So again, if I'm in dimension 2, it's quite easy. It's the same type of argument as what I was mentioning here. But in dimension 3, it becomes a bit more intricate, and you really need a varifold. So suppose that if you have a sequence En such that J of En is bounded, and En converges to E in L1. So if you assume that the boundary is C2, then you indeed have the lower semi-continuity of the function. So limit of J of En is larger than J of E. So surprisingly, this did not seem to be known before. It's actually just a, let's say, small observation, how you get that. So what was known was the isotropic case. So when phi is 1. And so how does the proof works? So basically, if you look at mu n, which is H1 restricted to the boundary of En, then by Allard, you have that mu n will converge to some measure mu, which will be integral rectifiable. So first thing is that mu will be bounded from below by H1 restricted to boundary of E. And mu is integral rectifiable with a curvature in L2. So H mu is the mean curvature of mu as a varifold. This is in L2. And what I mean by integral rectifiable means that mu has the form theta H1, here it's D minus 1. D minus 1 restricted to sigma, where sigma is a rectifiable set. Okay, now you want to prove the lower semi-continuity of the functional. So you look separately at both terms. So the curvature term, which is the harder one, has actually already been studied. So this is quite a deep result of Schätzler. And that's why you need this C2 hypothesis here to apply this result of Schätzler, which tells that the limit of the integral of h n squared is bigger than this. And now you want to pass in the limit in the first term. And so the kind of only observation here is that actually varifolds, they work exactly like Young measures. And so saying that mu is actually integral rectifiable. That means that if so instead of looking at mu n, if I looked at the associated varifold Vn, which converge in the sense of varifold to V, then V it's of the form mu tensor delta Tx sigma. And that means that as a Young measure, you have a Dirac mass in the limit, which is the same thing as saying that you have convergence if you think of functions. And so here is the same. That means that you don't have kind of oscillations on the tangent planes. And therefore, you have that for every phi, which is continuous, you can pass to the limit. So actually the limit of the integral of, let's see, good, phi of nu dh d minus 1. This will be equal to the integral of phi of t, so I don't know how to call it, nu sigma d mu, because phi is the admissible test function for the convergence of varifolds. And now, because of the fact, so now this, because of the, yeah, sorry, of the fact that the limit measure mu, yes, sorry. Okay, maybe I can add one step to make it clear. So here, instead of that, I will do phi of S v of xs when I integrate on Rd times the Grassmannian. So if you want to up to this point, you don't need to use anything. It's just the fact that phi is continuous, so you can pass the limit when you're testing against your varifold Vn. And now the fact that the limit varifold is rectifiable, that tells you this thing here is just the integral over sigma of phi of nu sigma d theta d h d minus 1. And now since theta is larger than 1 and sigma contains the boundary of E, so that's what I wrote here, this is larger than the integral boundary of E phi of nu dh d minus 1. And so you get the semi-continuity also of this part. Okay, so it's mostly observation, but it seems that it was not done before. And actually, I wanted to present the proof because it's also used in all the other results I will present after. So I think it's good to have the simplest version of that in mind. And of course, afterwards, I will not do it again. So. Okay, so now let's talk about phase field approximation. So we'll go slowly. We'll start. These blackboards are very difficult to move. Am I supposed to move them with a button or it's no, you don't know? Because it's extremely heavy. Okay, I don't want to break them. I know sometimes if you force on blackboard, it can be dangerous. Yes. Okay, so let's start with the simplest case where phi is 1. So I look at the isotropic model and delta is 0. Okay, so in this case, I just want to approximate the perimeter. So this is done classically using the Modica-Mortola approach. So I have W of t, which is the usual double well potential. So it's 1 minus t squared squared. And I'm looking at the integral of epsilon over 2 grad v squared plus 1 over epsilon w of v. So what probably most of you know is that this is converging in sense of gamma convergence when epsilon goes to 0 to a multiple of the perimeter. Where here you will have that v epsilon will converge to 1e minus the characteristic function of the complementary. So this is actually true for every dimension. It's not specific to dimension 2 or 3. And so what you have is that the phase field function will look like this. So this is my set E. And okay. I have a small neighborhood of the boundary where something is happening. So this is of size typically epsilon. And here inside, I will have v epsilon equal to 1, and outside v epsilon is minus 1. And in between, there's this optimal transition. And so if I look at just what's happening here, what I see is something like that. It's the usual hyperbolic tangent, which goes from -1 up to 1. So did I give it a name? I don't think so. It's my optimal profile, which is connecting the two wells. And it's a smooth function. Okay, so now let's stay isotropic, but look at delta non-zero. So, okay, maybe also for notation, I will call H epsilon. Maybe I can keep it there. So H epsilon of V, it's the part here which is approximating the perimeter. So it's epsilon over 2 grad V squared plus 1 over epsilon W of V. So I want to approximate now the mean curvature, also the Willmore energy or elastica function, depending on the dimension. And so for this, I will look at the first variations of the energy. So if I do the first variation of modica mortar, I find, okay, maybe I can write it here. Oh, sorry, this is not H, this is P epsilon. And now I have H epsilon of V, which is minus epsilon Laplacian of V plus 1 over epsilon W prime of V. And if I look at the first variation of the perimeter, I get H. So this is something which was suggested in a slightly different form by De Giorgi. Is that if I look at 1 over epsilon, the integral of H epsilon squared. Then this should be a good approximation of the integral of H squared. And so this was proven for dimension 2 and 3. So, by Matthias Röger and Erschatzel. And so actually, most of what I will present after is strongly based on this paper here, which is quite a deep paper. Okay, so this is for the isotropic case, but without with the curvature term. So now let's look again at delta equals to 0. So just the perimeter part, but for the anisotropic version. So see, I'm slowly getting towards my functional. Okay, so now I want to look at anisotropic. So phi different from 1 and delta equals to 0. Sorry, no, delta equals to 1. Okay, so this is a model which was proposed by Torabi and al. So this is a mechanics paper. And with my notation from there, they propose to look at f epsilon of v, which is the integral of phi of grad v divided by modulus of grad v. So this should be like the normal, time p epsilon of v, plus the integral of 1 over epsilon times h epsilon of v squared. See, so this term here is exactly the term I had before for approximating the curvature. And now this was the term approximating the perimeter. And the way that they say that you should take into account the anisotropy is in this form here. So there were other propositions before, but what you have to be very careful is that you need to have the same optimal profile for this part here of the energy and this part there of the energy. Otherwise, you will get kind of the wrong constants. So that's why they propose to add it like that, even though it creates difficulties because when modulus of grad V is 0, what does this mean? But okay, I will skip this question. There's a way to regularize a bit this part here. And so actually on the approximation, so on the justification, if you want, of this paper here, or the approximation of my functional J of E from that, there were some partial results by Lusardi. Where he proved that if you remove this part here, then this will converge to the relaxed version of the energy. And so what we could prove is that it's okay. So on smooth sets, so you still need this C2 regularity. So on smooth sets, you have the gamma convergence to what I call J. So this is phi plus square. So this is for dimension D equals 2 or 3. Okay, maybe a small comment on the hypothesis that the set is the limit set is C2, because we might see it again later. Actually, so you could imagine a larger class where you expect to have a semi-continuity, but these functional here, or like even if you just look at the isotropic version. This is not a lower semi-continuous functional on C2. Because for instance, if you have, if you are not on C2 sets, because for instance, you could construct dumbbells, so something like that. So this is my set En, so it's in 2D, which will converge to something like this. Okay. So as a L1 convergence, this is the same as converging to this thing without the middle segment. And you see that if I just look at this, this is not, it does not have a mean curvature bound in L2 as sets, but still can be approximated by sets which have perfectly fine energy. So this actually has been understood quite well in dimension 2 by Bellettini and Mugnai. So somehow, I mean, the C2 assumption is a bit annoying, but also you can't easily get that far away from it. Or if you want to get rid of it, you need to understand very well this type of phenomena, which in 2D are relatively well understood. In dimension 3, I don't think so. Okay, so that was about the perimeter type energies. So now let's go back to Mumford-Shah. Okay. So I talk about phase field approximation of Mumford-Shah. And so I will do the same story as before. So I will start by simplest case, so phi equals to 1 and delta equals to 0. So the way that it is traditionally done is through the so-called Ambrosio-Tortorelli approximation, which Flaviana already discussed a lot in a much more general setting. So I'll still go quickly on that. So the energy you look at is, so you introduce a second phase field variable, and you look at the integral of v squared grad u squared plus the integral of epsilon over 2 grad v squared plus 1 minus v squared over epsilon. So you see that where where V is 0, the grade U is not penalized, so it can be quite big, or you can jump. But you are penalizing the fact that V is not 1 by the term here. And so kind of this term here will give you a contribution which is like the length of the crack, and this will give you the elastic energy. But the reason why I want to talk about this is that in this case, if you look at the optimal profile, so the optimal V here, a bit like what I showed here, it will have the following form. So something. In particular, a very important aspect for us is that this V is not in H2. And since V is not in H2, it's not good for approximating the curvature type energies. And so you need to do something to go around this issue. This is actually a problem which is known for a very long time. And so one possibility, which I think was suggested in the paper by Brides and Mark, is to kind of go back to a more standard Monica-Mortola type energy in the following way. So if you want, what you had in mind is that you have this crack, so this is JU, and then you have V, which is 1 on both sides. And you want to approximate that by something which looks like this. So you have V equals to 1, and V equals to 1, and here you have V equals to -1. And you have now two transitions. You have one transition here, and one transition there. And you want to make sure that the size here goes to 0. Okay, so the proper hypothesis is that epsilon log epsilon over eta epsilon goes to 0. You can already forget this. And what you take as energy is the integral of 1 plus V squared, grad U squared, plus the integral of P epsilon of V. And then you add something which is going to force V to be equal to 1 almost everywhere, which is 1 over eta epsilon times the integral of 1 minus V squared. Okay. So you see that in theory, when I'm just looking at this functional here, the phases 1 and -1 are symmetric. But by adding this factor here, I'm forcing in the limit V to be equal to 1 almost everywhere. So if you are just interested in the Mumford-Shah functional, this is not such a great idea, because of that, you see that the size where you don't have a sharp interface is much bigger than before. Before it was size epsilon, now it's kind of epsilon log epsilon. But okay, you just lose a log epsilon. So another possibility was proposed extremely recently, so a few months ago, in a paper by Bretin, Chambol, and Masnou, which, to say it very quickly, is to detect these one-dimensional objects by looking at the derivative of the optimal profile for the Modica-Mortola energy. But I will not talk too much about that. I think it's 25. It's either 25 or December 24. Okay. And so maybe just to comment, you see here again, if V is equal to -1, so in this region here, grad U is not penalized. So again, it can be quite big, and that leads to the creation of the jump set. Okay, so if you look away from the endpoints and multiple junctions, the natural proposition to approximate where am I? Yes, so I still want to approximate. Yes, okay. So now I do still phi equals to 1, but delta equals to 1. So I want to add the curvature term. So away from endpoints. So the natural thing is to look at the integral 1 plus v squared radius squared plus the integral p epsilon of v plus 1 over eta epsilon, the integral 1 minus v squared, plus 1 over epsilon, the integral of h epsilon of v squared, where I recall you the notation from here. And now the big question is, how do you incorporate the points? I think this is kind of maybe the most interesting part of this. So from here onwards, I'm only talking about dimension 2. Okay. And so the idea is to kind of do a second Ambrosio-Tortorelli type approximation, which is going to be for the points. And so you want to kind of multiply the term here by something which is not going to penalize it when we are close to the points. So I'm saying that you introduce a new phase field, W, and I will replace the integral of h epsilon of v squared by the integral of 1 plus W squared h epsilon of v squared. And so where W is equal to -1, I will not pay the term here, and so I can actually take it big. And now you want to penalize the fact that you have W different from -1 away from points. And so the idea comes from a paper by Brides and Malchiodi, or Brides and Mark. If you want a remark. This is already in the paper by Brides and Mark. And see also Brides and Malchiodi. So it's based on the famous inequality, a squared plus b squared is larger than 2ab. So now if I want to look at the minimum overall, let's say set in C2 of beta, the integral of h squared on boundary of E, plus 1 over beta, the integral, the boundary of E of 1. So this is the perimeter. If I apply this inequality here, so sorry, this one I will write as the integral on boundary of E of beta h squared plus 1 over beta by Young's inequality. This is larger than 2 integral boundary of E of h. And now you have Gauss-Bonnet. So this is larger because you will get the same constant for each connected components on the boundary of 2 times 2 pi, so 4 pi. So this is Gauss-Bonnet. So you have a universal lower bound on this energy here, and you can even compute the minimizers. So if now I take E to be a ball of size r, then you can do the computations. See that the curvature is like 1 over r, so I have beta times, so 1 over r squared times r, it's 1 over r, so beta over r, plus beta times r, sorry, 1 over beta, r over beta, and all this times 2 pi. Now, if you optimize, you see that, of course, the solution is to take r equals to beta. And when r equals to beta, this is 1 plus 1, so you get a 2, so you get this is 4 pi. Okay, so if you take a disk of radius beta, then you get exactly that this energy here is equal to 4 pi. So if I want to penalize, let's say, 4 pi times the number of points, I can just add kind of this energy here around every point. Okay. So now I will take a phase field which will approximate this. So I will add to what I have up there kind of the natural phase field approximation of that. Okay. And send beta to 0 at the same time as the rest. Okay. So now it's time to write the full phase field model, I guess. Okay, so I will directly write the anisotropic version. So the functional we look at is the integral of 1 plus v squared grad u squared plus the integral of p epsilon of v phi of grad v over mod grad v plus 1 over epsilon the integral of 1 plus w squared h epsilon of v squared plus beta. So now comes the part which is the approximation of this. So beta integral of h epsilon of w squared. So this is the curvature term, but for the phase field variable w, plus 1 over beta integral of p epsilon of w. And then there are the two terms which are here to force v and w to go to 1. So 1 over epsilon, eta epsilon, sorry. Integral of 1 minus v squared plus 1 minus w squared. Okay. And actually, if you forget the anisotropy, this functional was explicitly suggested in the paper by Brides and Mark. So that paper was written before the Röger and Schatzler paper. And so they prove a phase field convergence for a different model, which is slightly more complicated. And they say, okay, it would be nice to prove gamma convergence for this one. But as far as I know, nobody did it. And so the theorem is that it works. So I will not write the precise theorem, but again, if the limit is a finite union of C2 curves, and I mean you can incorporate the crack tips and the multiple junctions, then this functional here is indeed gamma converging to the functional I wrote in the beginning, which I will not write again. And so maybe one remark before I talk a bit about the proof, very briefly. Is that, as far as I know, in the business of the Georgi type approximation of curvature functional, is the first time that you can also have singularities. Of course, they are very controlled singularities and they are built in the model, but usually it only works for a C2 set. So it was interesting to have something which is working also when you have these singularities. So maybe a few words. So I should stop in 5 minutes, I guess. No. Yes. So sorry. Yeah. Good. So the main, I think, interesting part of this work is how you deal with the points, and especially how do you get the 4 pi constant here. I mean, there are two funny parts. So what you can prove, so let's call G epsilon beta of W. That's just the part for the point. So beta integral of h epsilon W squared plus 1 over beta integral p epsilon of W. Then you have the following dichotomy. Either, so if W epsilon minus 1 does not converge uniformly in a given ball to 0, then you can prove that the limit of G epsilon beta W epsilon, let's say in slightly bigger ball, this is larger than 4 pi. Okay. So this is saying that either the part which is coming from this phase field variable W epsilon is not playing any role in the curvature part of V, or if it does play a role, then already from the point part, you need to pay at least 4 pi. And so after appropriate blow up, it's enough to consider beta equals to 1. And using the Röger-Schatzler result, you get that mu epsilon. So this is h epsilon dx. This is converging to some v, which is integer rectifiable in L2. And sorry, this is h v in L2. And you have that the limit of g epsilon of w epsilon, this is larger than the integral of 1 plus h v squared d mu. And again, you can do the a squared plus b squared trick. So this is larger than 2 integral of h d mu. And now the problem is that you would like to do something like Gauss-Bonnet, but for varifolds. So one observation, which I learned in the paper by Marco Pozzetta, but which maybe also follows from work from Ulrich-Menne, is that using the monotonicity formula, so for varifolds with curvature in L2, it's quite easy to prove that you have this larger than 2. The problem is that 2 is strictly less than pi, so it's not enough. And actually, to go from this 2 to pi, you need a proper generalization of Gauss-Bonnet for varifolds. And actually, this was somewhat already done by Ulrich-Menne. So Gauss-Bonnet for varifolds. So there is a very long preprint of Menne from 2014, where he proves this. Okay, in that preprint, it's only written for dimension 3 and higher. So we actually had to go through his proof and kind of check that it's working and maybe simplifying a bit the proof because we're in dimension 2. But yes, so it does work. And I think this work of Menne deserves more publicity. I think it's not very well known. It's actually not so easy to find also the proper statement, but it's a very impressive work by Menne. And the main difficulty in this proof is to show that the Gauss map has the so-called Lusin property. So if you have a set of measure 0, and you look at its image on the unit sphere by the Gauss map, then this will still be of measure 0. And this is an extremely difficult thing to show, at least in this case. And okay. Maybe I should stop here. Okay. Another thing to say, but I think I will skip it and we'll stop here.
Questions? No questions? Ah,
You always said C2, you really cannot do anything if you have some sort of cusps. Sorry, can you do anything when your domain may have some cusp or I mean, try to imagine. Your E was the beginning, right? Was C2. Can you do
Yes.
something where you could have not C2? Anything.
I mean, it depends on the question, let's say. When you start to look at the phase field energies,
Yeah.
because I mean, if you're just interested at the sharp interface problem, if you're in dimension 2, you don't really need to use the whole machinery of varifolds. And then you can say more, in particular, using the work of Giovanni Bettini and Mugnai. So they understood quite well what you should do there. But as soon as you start to look at the phase field version, then there, as far as I understand, you need to go through all this varifold theory. And there, to prove the lower semi-continuity result, you need this result of Schatzler, which needs something like C2. I mean, okay, maybe say C2 rectifiable, something like that. So we very heavily rely on that. And
Okay.
I think answering your question goes beyond my knowledge on this problem.
Thank you. Thank you.
I was just a curiosity. So how does the phase field looks like? So
in which sense?
Should be like something, a phase field on the interface and then some balls on the endpoints?
Yes, I mean, you have a two-scale problem. No?
Okay.
You have one scale which is describing what's happening next to the crack. Then you have a smaller scale which is close to the points. So we have kind of this two-scale type of picture. We haven't done any numerics. So
that was the other question. Okay.
Would be very natural and good. But,
the second speaker of this afternoon section is Emanuele Radici, who will talk about characterization of area strict limits of planar BB homeomorphism. Please.
Do you hear me? Yeah. Okay, so thank you very much, Riccardo, for the introduction, and also to the organizers for the very nice conference, first of all, and also for the kind invitation. It's always very nice to be in Pisa, especially in summer. Okay, and this week better than last week, I was told, because now at least there is some wind and less degrees. Okay, so today I would like to talk about some works that we have in collaboration with Daniel Campbell and Apo Kauranen. Daniel Campbell is in Prague, and Apo Kauranen, he just quit academia after our work together. I hope it was not my fault, but he was in Jyväskylä. And it's about the characterization of area strict limits of planar homomorphisms of bounded variation. So I will tell you better what I mean by these area strict limits, because area strict, I guess, is a typical word in this title. But before going there, I would like to start from some motivations why I ended up studying this closure class of homeomorphisms. And spoil motivation comes from nonlinear elasticity. Probably this kind of introduction has already been done many times yesterday and this morning. But the typical problem in nonlinear elasticity in general consists in the following. You are given two domains in Rn. We can imagine them to be nice, so open bounded, super nice, with super nice boundary connected and so on. In general, you can consider, okay, let's assume also that there is a prescribed way on how to modify the boundary of the first domain, of the first configuration omega, onto the boundary of the second configuration delta. And this prescribed way on how to modify the boundary is super smooth. For example, a diffeomorphism, fixed, okay? And among all possible ways on how to deform, let's say, the interior of omega onto the interior on delta with this fixed boundary, extending this fixed boundary, these deformations are elastic deformations. What is an elastic deformation? Is a reversible shape change of the material. Okay, so the proper mathematical concept that describes these features of the elastic deformation is that of homeomorphism. Okay, so continuous and invertible. Okay, we consider all possible homeomorphisms extending this fixed boundary datum in the interior of omega onto the interior of delta, and among them one looks for those who are minimizing energy functionals of this form. Okay. This is the case of hyperelasticity. I'm accounting only for the bulk term for example, in comparison with what was said in the previous talks. And okay, in order to have some physically reasonable model, clearly one has to impose some conditions on this stored energy density W that make it realistic in the sense that they, for the minimizers, avoid unrealistic behavior. So for example, since in elastic deformations, no interpenetration of the matter is allowed, then a request is that whenever the determinant of the gradient of your displacement, of your deformation, is negative, then the energy is plus infinity, okay? And also, other two assumptions, like realistic assumptions, are that, let's say, optimizers are avoiding extreme behaviors, in the sense that when you want to compress too much a material, okay, so the determinant of this gradient is going to 0, then the energy blows up. And the same also when you want to apply an infinite stretch, okay? And then there are also other assumptions that you can make on this energy in general that is rotation invariant, and also as soon as you apply something, then you pay a cost with respect to the identity. But okay, let's stick to these three, for example. And so a typical choice for this functional in the applications is some stored energy which behaves more or less in this sense, so is controlled from above and below by this sum of terms for some p. So we are we are counting for the LP norm of the gradient, and some function phi of the determinant, where phi is some convex function, which is then exploding, blowing up as soon as the determinant, so the variable, the argument is going to 0. Okay, to recover this assumption on the high compression. And a choice is, for example, this ratio here with the determinant at the denominator, but it's not the only one. There are many choices in the applications. So anyway, this term has to do with the LP norm of the gradient of the inverse of the deformation, whenever this makes sense. So now, if I call theta p the class of homeomorphisms, so for me they will be the elastic deformations, the class of homeomorphisms in the correct Sobolev space, according to the p appearing in the energy, which are extending the fixed boundary datum, then these problems, the variational problem, is as looking for a minimizer, the infimum, a priori, of this energy on the class theta p, okay? Just to set the notation. And clearly, this problem is very different depending on the relation between the regularity, so the p, the exponent, and the dimension, okay? When p is bigger or equal than the dimension, actually the density is naturally, under these assumptions, is naturally coercive and lower semi-continuum in Sobolev. Then the question, so by direct methods of calculus of variations, we get the existence of minimizers in Sobolev. The problem is whether they are also one-to-one or not, whether they are invertible or not, whether they're truly elastic deformations, so homeomorphisms. And actually, John Ball, at the beginning of the 80s, who had this pioneering result, which kind of gave rise to this theory, providing a yes. When p is strictly bigger than the dimension, yes, there exists a minimizer that is not just Sobolev, is in the class theta p, okay? Now, when p is equal to the dimension, actually the problem becomes more complicated, actually, under some very strong assumption on a notion that is that of mappings of finite distortion, when we ask a lot of integrability on that, and we ask something more about the boundary. So rather than just being equal to your prescribed deformation on the boundary, you have to be equal to a diffeomorphism on something that is of strictly positive measure, not so something extending the boundary already inside. Then one can actually prove that this problem is also well posed there. But the case that we in which we are more interested today is that of the subcritical case. So when P is less than the dimensional, and so when the functional is not anymore lower semi-continuous, so just it's not possible to get the existence of minimizers in W1P simply via the direct method. And so in general, one has to come up with new ideas, and one has to consider bigger classes of deformations. There are in general two approaches to this subcritical case. One approach, of which I confess I'm not super expert about, is that of considering, let's say, a different problem from the beginning. So more or less similar energies, but with already a class of deformations which is not that of homeomorphisms. And here are, for example, like this is the perspective of Müller and Spector and of a series of work by Henao and Mona Corral. Okay. The other, there are, I think, even more recent results, existence results with, from this point of view, also involving Henao, Mora Corral, Barchiesi, Remiro Diac, and others of that school. Let's say the approach I want to focus more on is the other one, that is, okay, instead of changing the problem, let's try to look for relaxations, okay? And so for relaxations of the energy and understand who is the corresponding closure of the class theta p, of the class of homeomorphisms with respect to the topology you use for the relaxation. And okay, then here there is a big difference depending on whether P is strictly bigger than 1 or equal to 1. When P is below the dimension but bigger than 1, then one way to standard standard relaxations of this functional is is just taking the Sobolev, yes, to do the standard lower semi-continuous relaxation functional through Sobolev, the Sobolev W1P, In the relaxation, you just need to recover the lower semi-continuity because coercivity is already granted by the fact that P is strictly bigger than 1. Okay, then it's only needed to understand who is the class, the closure of the class theta P with respect to the topology you use for the relaxation. Now, when P is equal to 1, you lose also the coercivity for your functional, okay? And so in the relaxation, you have to recover also the compactness, so the coercivity. And so the relaxation has to occur in BV, okay? And the first idea, naive idea could be, okay, let's relax with respect to the weak star topology in BV. But this is not a good idea if you have in mind elasticity. Why? Because in elasticity, you expect that the image of the disjoint sets, okay, is still essentially disjoint. You have this request on the non-interpenetration of the material. So in the worst case, you collapse some masses somewhere, but you will never interpenetrate it, okay? And while with weak star relaxation, you actually allow for this unrealistic behavior of the weak star limits. And here is a construction which it describes more or less this behavior. Let's assume to have omega and delta in this case are the two unit squares with the identity on the boundary, okay? And let's assume to have this sequence of homeomorphisms, of deformations, on which you have to read it in this way. So and the first one is deforming, and I am comparing the colors. So I'm deforming this yellow square onto this stretched rectangle yellow, and the green part is squeezed on this side, okay? And here I just, this transition part is just to have everything continuous, okay? But the stretching is happening in this internal layer, and I'm doing this more and more in a thinner and thinner rectangle inside my square to the limit, okay? In the limit, what I'm doing, I'm just the identity everywhere, and I'm mapping this, I don't know if you can see it from far away, this yellow point, the left extreme point of this segment is mapped on the whole segment here, while the green segment goes to a point, okay? Now take this construction and do it rotating it, okay? So if we take this construction and we repeat it rotating, and we take a good subsequence or a diagonal subsequence changing the angles, actually what one can produce is a sequence of homomorphisms whose limit is doing exactly this. So it is the identity literally everywhere but in the center of your unit square, and the image of the center is this disk. Okay, so here you are violating this non-interpenetration of the material, because if you take this disjoint ball with strictly positive mass measure, so some volume, then their image is actually overlapping on some positive measure. Okay, and this is something that you don't want to see. So what's the problem here is that we are relaxing with respect to a topology that is too weak for elasticity. And so has to, when p is equal to 1, one has to look for relaxations which are less weak in some sense, still in BV but less weak. And two good choices are the strict topology and the area strict topology. The strict topology, probably you already heard about that. Your a sequence of mappings is converging strictly to a limit in BV if they are converging as measures, and if the total variation of their gradients is converging to the total variation of the gradient of the limit. Okay, while the area strict topology asks for something more. So you are converging area strict if you are converging as measures in BV, but you are asked on top of that that there exist two sequences of measures. I'll call them mu j and nu j, for which their sum is equal to the gradient of uj, of the approximating sequence. And mu j is approximating strongly the absolutely continuous part of the gradient of the limit, and nu j is approximating strictly the singular part. So you are doing the best as you can. You are a weak type topology, but which wants to be strong as soon as this is allowed. So not where you have the singular part of the gradient. And clearly by the definition it's clear that area strict implies strict. Why the name area? Because there is a nice characterization of this convergence in terms of the area functional, where here you have you consider the absolutely continuous part of the gradients of the approximating sequence, and here the singular part. No, in principle, no. In principle, no. Okay. No. Okay. You can even have that, for example, these are super regular, but you have sum of two parts, and one that is still absolutely continuous is producing the singular part in the limit. Okay. Okay, and I told you area strict implies strict, but the converse is clearly not true. This is a very easy counter example. In the 1D, for example, take the function, here the limit function is 2x on the interval 0, 1. So on this side, we are approximating 2x with jumps, okay, with piecewise constant functions which are jumping. Clearly, here the total variation of each element of the approximating sequence is 2, okay, and the very same is for the limit, okay. So we have clearly strict convergence, but we don't have area strict convergence, because if you check with this characterization with the area functional, in the first case, I don't have absolutely continuous part of the approximating sequence, so this counts just as 1. And here I'm doing a jump of 2, so this term is always equal to 3. While in the other case, I just have absolutely continuous part and not the singular part, and so I'm seeing 1 plus the square root of 1 plus 4. Okay? So, okay, this is not a counterexample with homeomorphisms, but actually one can also have a counterexamples with them. Now, why I quoted these two kind of topologies in BV? Because there are two results, 3 actually, of about relaxations. Yes. And as I said, there are two relaxations, 3 relaxation results about energies of the form I was talking about before with the bulk term in the linear case, so p equal to 1. One is due to Christensen and Rindler, for which they provide a BV relaxations of those functionals with respect to this strict convergence, and then this was for Dirichlet boundary conditions. Then there was an extension due to Bahia, Kromer, and Kruschik for more complicated boundary conditions, and then also another result of Rindler with Gilles Shaw, who refined the argument to get that the continuous extension works also with respect to the area strict topology. So it was exactly Rindler who suggested me to look for the class that I'm going to describe in a moment with respect to these two topologies. So because of this, actually, we are naturally led to study various classes arising as limits of elastic deformation, so as limits of homomorphisms. And in this context, when p equals to 1, then it makes sense to study the closure, okay, of homomorphisms in W11 with respect to the strict or area strict topology, okay? So this was just as a motivation. Let me tell you that actually there has been some activity, let's say, in this problem about the diffeomorphic approximation of homomorphisms. Okay, so how to approximate elastic deformations with smooth elastic deformations in the past years. There is this result of Aldo Pratelli and Stanislav Ensel. Okay, from now on, I will just talk about the planar case. Okay, so from now on, n is equal to 2 and p is equal to 1. So where they prove that actually every homomorphism in W11, so the kind that we are interested in, can be strongly approximated in W11 by diffeomorphisms. Okay, this is not easy at all. When you want to approximate functions with smooth functions, you just convolve and you're done. With homomorphisms, so you have to preserve injectivity. So as soon as you convolve, you lose that. It doesn't work. So this is really not an easy question. Okay, and but they are able to prove to approximate every homomorphism with diffeomorphisms is in W11. So looking for the closure of this class with respect to area strict or strict is the same as looking for the same closure in the class of diffeomorphisms. Okay, and during my PhD, actually with Aldo Pratelli, we tried to obtain the same result of Ensel Pratelli, but in the case already of BV homomorphisms, not in W11. And we were able to prove the same in the sense that every homomorphism in BV, not W11, but directly in BV, can be approximated in these two topologies, area strict and strict, by diffeomorphisms. Okay? And so actually, since these are the two classes we are interested in, they're equal to those, but those are equal to those. So in the end, the classes that we want to discuss are these two. So the strict or area strict closures of homomorphisms with bounded variation, which are extending a fixed boundary datum that you can imagine it to be the identity, okay? Okay, so let me say a few words about previous results about the closure of diffeomorphisms, of homeomorphisms, sorry. In the Sobolev case, the first result, planar always, n equal to 2, the first result is due to Ivanets and Onninen, where they actually proved that they were the first ones studying the diffeomorphic approximations of homomorphisms in Sobolev for p bigger or equal than the dimension, so p bigger or equal than 2. And they were able to characterize the weak and strong closure of the homomorphisms, which is the same as the weak and strong closure of the diffeomorphisms. And in the end, what they obtain is the subset, if you want, is the class of W1P maps, which satisfy the inf condition, or they are monotone maps. Basically, what does it mean? That if you take the boundary of a ball, okay, and you consider its image, okay, a monotone map is mapping what is inside the ball into the interior, okay, of the Jordan curve that of the continuous image of the boundary, okay, and what is outside stays outside, okay. So they found this characteristic feature describing, characterizing all maps which are limits, weak or strong, of W1P diffeomorphisms. Okay, when you go below the dimension, there is a more recent result of Guido De Filippis and Aldo Pratelli about that, and they can still prove that the weak and strong closure of diffeomorphisms, even below 2, are the same, and but actually the inf condition, so the monotone mapping condition, is too weak to describe this class, so they had to come up with another characterization, which is the following. I'll discuss it later, is the non-crossing condition on maps. And clearly in this case, as soon as you go below the dimension, the limit configuration, so the limit of diffeomorphisms, or homomorphisms as you want, they are not continuous anymore, but the discontinuities are very precise. They are cavitations, okay? So you are opening holes, okay? And they are only, I don't remember if countably many or finitely many, but countably many. Okay, then with Daniel Apo and also Stanislav Ensel, we started studying the strict closure of homomorphisms in BV, okay? We actually show, so I told you that with respect to weak star closure, we get things which are not realistic, okay? So we started studying the properties of the strict limits, and we could actually prove that this bad behavior about the non-interpenetration of the material cannot happen. And we have some nice discontinuities that we actually really expect, which are cavitations, as in the Sobolev case, but also fractures. Okay, here fractures can occur. And then in several works with just Daniel and Apo, we are able to characterize this closure class, both in the strict and in the area strict case, which consistently with the Sobolev case, we can actually prove that, okay, these closures, for what I told you before, are exactly the closures with respect to the same topologies of the diffeomorphisms W1P, W11, okay? They are the same, okay? More or less, this is the weak and this is the strong closure, okay? And we can characterize the limit class with this condition, which is, with not much of inventive, is the non-crossing BV condition of maps, okay? Because the non-crossing condition introduced by De Filippis and Pratelli doesn't work directly in our case because our mappings are way more discontinuous. So we have to be able to treat these discontinuities. Actually, what I just said is partially, I was cheating a bit in the sense that what we proved with Ensel and the first paper with Apo and Daniel was about the Manhattan strict topology and not the strict one, where the Manhattan strict basically the sum of the first derivative and second derivative. So the derivative with respect to the first component and the second component are converging, okay? So the Manhattan norm of a two component function vector is the sum of the modulus of the two components, okay? So in principle, this topology is weaker than just the strict ones. And still these two coincides. Okay, so the concept of topological image of these continuous functions was already introduced by Müller and Spector, but basically so it's okay when you have very few discontinuity. In our case, H0 measure of discontinuities. Our BV maps may be discontinuous also on something which is which has H1 measure strictly positive, and so we had to kind of come up with a new definition of topological image for our functions, and we did that using the approximating sequence. Okay, so what we do, we define a proper multifunction which contains all the possible limits of all the possible sequences converging to the points. Okay, so the situation is that we have an approximating sequence of homomorphisms, okay, and a limit BV map F, okay, and we define this multifunction which contains all the possible limits which are produced by the approximating sequence. And what is nice is that there is this nice geometrical characterization of this multifunction. And what is even more nice is that this multifunction doesn't depend on the approximating sequence. It's always a closed, non-empty, and connected set for every x. Is a singleton for almost every x, as you expect. Okay. Also, we can prove that the function, the limit of the strict limit of BV homeomorphisms is always differentiable almost everywhere. It allows for a sort of inverse in the sense that when you have an homomorphism in BV, in a planar homomorphism in BV, also the inverse is still an homomorphism in BV. So it makes sense to look for the weak star limit of the sequence of inverse of these homomorphisms. And actually the multifunction connected to the inverse of this limit here coincides with the proper multifunction that we introduced before. And the very nice thing is that in terms of this multifunction, the image, the topological image of this joint ball is essentially disjoint, in the sense that, sorry, this one indicates the L2, the Lebesgue measure of the intersection of the two images is 0. Okay, so they can collapse on something which has a strictly smaller dimension, okay? But they cannot overlap on something which has positive mass, okay, positive measure. Also, so these two things I just said, let's say for these BV mappings, let's say it's not possible to talk about distributional Jacobian because they are too discontinuous, they are too irregular. But for the approximating sequence, we can. So we can define a sort of distributional Jacobian as a measure, as a limit of the distributional Jacobians of the approximations. And what we can prove is that this limit Jacobian measure, is measuring in the image the Lebesgue, so the area of the set described by the multifunction. For example, if you have a cavity, okay, which is open a hole in the image, the limit distributional Jacobian at the cavity point is measuring exactly the surface of this opening in the image. If you have a fracture, okay, then the topological, the multifunction of a fracture point is describing the segment connecting the jump, and so this one is actually, oh, sorry. And here, this one is measuring the length of this jump, okay? Now, so if you have a full line, a fracture line, then you are, this Jacobian is measuring how much you are opening the fracture, okay, as a two-dimensional set in the image. Okay, and I already told you that we get both this kind of discontinuities, cavitation and fractures, and also on fractures we can, they are one rectifiable, and we can bound the length of the fractures in terms of the energy bounds, so on the total variation of the derivative of the limit map f, which is BV, so it's finite. And actually all we just said for strict limits is the very same for the Manhattan strict limits, okay? Nothing changes. Now, what is the NC condition that I mentioned before? The non-crossing condition for a BV map looks more or less, is more or less this. So basically you take, so let's assume that our reference and target configurations are squares, okay, with the identity mapping the boundary on the boundary, okay. Then the non-crossing condition, your map satisfying the non-crossing condition satisfies the following, basically, that you can take any grid, okay, in your first unit square, okay, as fine as you want, with as many sides as you want, okay. Avoiding countably many points. Okay, so this grid is allowed as soon as you avoid a set of H1 measure 0. Okay, you look for the, you consider the image of this grid. Okay, so remember that they introduced this concept for Sobolev maps, so they didn't have too much problems with respect to the continuity. They could be discontinuous just at countably many points, okay? So the image is the standard image, okay? Then being non-crossing means that you are always able to injectify, okay, the image of a grid, okay, being very close to the initial image, uniformly close to the image, okay? So, okay, for every grid, avoiding countably many points, you have an image, you can injectify this image being very, very close to the original image, okay? Very, very close uniformly. Okay, then non-crossing is actually something stronger than monotone, I already said it before. Actually, with Daniel and Aldo, we tried to come up with a more handy notion characterizing the Sobolev closure of homeomorphisms, which was the non-crossing condition on lines. Rather than looking on this injectification on grids, we wanted to do it on lines, but we failed. Actually, it's not true. This NCL condition doesn't even imply inv. But if you on top assume that the determinant of your maps is positive almost everywhere, this is true, okay? Which is something that is very often considered in elasticity. So maybe this can be useful somewhere. And as I told you, in general, this is not even true that the NCL implies inv. Now, what is the NCBV condition? Actually, we don't have this nice property of continuity outside countably many points in BV. We can be discontinuous on some sets which have H1 measure positive, okay? And so we want to ask for something similar on grids, okay? But we cannot ask our grids to avoid the discontinuity points, okay? So what will happen is that fracture lines, fracture curves may cross the grid that we consider. What we can ask is that the crossing points of our grid are not on a fracture line, okay? Because the crossing points are only countably many, finitely many. And then what we do, we use the multifunction to define an image of this grid, okay? And then we parameterize this image curve, okay, described by the multifunction, with a continuous mapping G, which I will call continuous parameterization, which keeps as much information possible from the original function, okay? And then we require this G to satisfy the non-crossing condition. So now, this, and we call this NCBV. so with a picture is easier. So we have our unit square, which is so with the function that goes from the unit square to the unit square being the identity on the boundary. We take grids. Okay, this function can be discontinuous on something which has h1 measure positive, for example, on these two violet lines. Okay, our grid can cross these lines, okay, these discontinuity curves, but the important thing is that the crosses of our grids are not contained in the bed set. Okay, then what do we have? We have an image, okay, which which can be discontinuous clearly, okay. Through the multifunction, we connect the discontinuous point somehow, okay. And then, so up to now we just have curves here on the image. We have to parameterize this. The role of G is that of parameterizing this, trying to be as close as possible to the original F. Clearly it will not be close on the jump points, okay. And then we ask this G to be injectifiable, okay? This is the non-crossing BV condition. And with Daniel and Apo, we first prove that basically this property of being NCBV characterizes the Manhattan strict limits of BV homeomorphisms. So whenever you have a function f of being a map of bounded variation from the unit cube to the, from the unit square to the unit square being the identity of the boundary, that satisfy this NCBV condition, then it is the Manhattan strict limit of BV homeomorphisms, extending the same boundary datum. And I recall here is the Manhattan convergence. And and also at the same time, every f that is obtained as a Manhattan strict limit, extending the identity, is an NCBV map, okay? And we can improve this by proving basically the same result, but with respect to the area strict limit, okay? The area strict topology, sorry. So I would like to give you an idea of how this works. And okay, so let me prove the easy implication from Manhattan to NCBV. So we start from the assumption, the situation in which we know that our F is approximated by a sequence of homeomorphisms Fk in the Manhattan sense. Now, basically, so in the Manhattan sense, it means that on almost every horizontal line or vertical line, the restriction of Fk is still converging, okay? So we can choose a grid of horizontal and vertical segments in our square Q, where the convergence, the Manhattan convergence is still true, okay? It's true for the restrictions. And then we consider the topological, the multifunction, sorry, being the topological image of F in the way I explained you before, which takes into account all the possible limits, okay? And the continuous parametrization of the multifunction as I described it before, okay? And what we want to prove is the NCBV condition. So we want to prove that this G is injectifiable, right? So we have to construct the injectifications somehow. And what do? We simply use the approximating homeomorphisms. So basically, we take the restriction of Fk of the approximating homeomorphisms on the grid. And what happens is that for many, many points on the grid, your Fk is converging to F. Okay. And what you can prove is that basically the image of Fk through gamma is contained in a neighborhood, okay, of the multifunction describing the image of gamma through F, okay? And then simply at this point, you define the parametrizations starting from these ones and being uniformly closed. Okay, this is very simple. You have the approximating sequence, you take the approximating sequence on your grid, you look at what happens in the image, and you refine a bit the things in order to be close to the proper multifunction. And it's super easy. Clearly, I started from the Manhattan strict to the NCBV because the case area strict implies the NCBV now is immediate because area strict is stronger than Manhattan. Okay, what is much less easy, so it's the other implication. So starting from a map which has the non-crossing BV condition, prove that this can be approximated in the area strict sense by homeomorphisms. Okay, and here we have to use two superfine results on BV mappings. The first one is very well known, especially in these days, is Alberti theorem, which tells you that in the polar decomposition of the gradient of a BV map, then actually the matrix is rank 1. Okay, is rank 1 at almost every singular point. Okay, and the other is Federer-Volpert theorem, which is telling you, okay, at those points, so or at least or except a zero measure of these points, then your jump is exactly you jump exactly in the direction given by the rank 1, the direction described by the polar matrix, and your jump counts as F plus minus F minus there. And why are these two results crucial? Because, okay, we are in this situation. So we have a mapping F, which is mapping the unit square to the unit square with the being the identity on the boundary. This is NCBV, okay? And so the set of discontinuity of this F can have a H1 measure positive, okay? And let me call the bad set of discontinuity points S, okay? Which can be something, I don't know, of this form, okay? This S, we can kind of cover it somehow with squares, with very small length sides, in such a way that on these on each of these squares, the singular part of the gradient of F is very much concentrated, okay? But the absolutely continuous part is very small. So up to take the length side small enough, okay? The absolutely continuous part of the gradient can be as small as you want, but the singular part is all concentrated there, clearly, okay? And basically, we have to be careful in choosing these squares. Not just the length side is important, but also where we take them. And this is the other crucial thing, is that we can choose them in such a way to satisfy a sort of Lebesgue point time estimate for the singular part of the gradient. Okay, so this thing, so taking the absolutely continuous part small, is in this sense. So the absolutely continuous part of the gradient on each of these squares counts as an epsilon times the singular part, okay, which is the one that counts. While this Lebesgue point time estimate says the following, says that in each of these squares, okay, basically there is a preferred direction. So your the singular part of the gradient is close to a rank 1 matrix, which is giving you a preferred direction, if you want, in which your singularity is moving, whatever this means. So up to take the square small enough and this more or less around the center, so centered in some good points, then all the singular part of the gradient is wants more or less to behave as this jump, okay? Wants to go in this direction, okay? This is a sort of Lebesgue point type condition for a generic function. Here we are doing it with instead of Lebesgue, we have the total variation, okay? And yeah, okay, we don't have a function, but we have the singular part of the gradient. Okay. And now we call sigma the union of these small squares which are covering the bed set. Okay. And up to take the side lengths smaller and smaller, this sigma has a very small measure. Okay. And now, so what do we have now? So this is the sigma. Okay. So outside sigma, we have very few singular, very small contribution of the singular part of the gradient. So we are basically a W11 map. Okay. And so being basically a W11 map means that the NCBV condition is basically the NC condition. And so we can construct, so remember what is our goal? Our goal is to construct homeomorphisms which are approximating area strictly. So here outside, you don't have the singular part of the gradient of f, so here outside you have to approximate strongly. Okay, the area strict is approximating strongly there. Okay, so we basically follow the ideas contained already in the De Filippis Pratelli to construct the strong W11 approximations there. Okay, so basically what we do is once we have these squares composing sigma, we extend them taking a grid, okay? And in the rest of the grid outside sigma, we more or less do what was done in the De Filippis Pratelli, okay? And we are able to construct the homeomorphisms which outside sigma, okay, approximate strongly the absolutely continuous part, okay? Which is basically the total gradient of f, because outside of sigma, the singular part is as small as we want, okay? And now what do we do on sigma instead? On sigma, the sigma is the bad part, okay? So we have to find a way on how to define the homeomorphisms inside each of these squares composing sigma, in such a way not to destroy in such a way to approximate strictly the singular part of the gradient, okay? And what I didn't tell you before is that, okay, once we complete the grid, okay, what we do, we have an image of the grid clearly. This image can be very collapsed because the function is just NCBV, but the fact that the function is NCBV tells us that we can always injectify the grid, okay? So here we will have some injectifications of this grid due to the NCBV conditions, okay? Then for what was the grid outside sigma, we need to change these injectifications to recover the construction that De Filippis and Pratelli do. And in particular, one step will be to piecewise linearize the injectifications. But then some of the squares coming from this piecewise linear approximation of the injectifications will become the boundaries, basically, the images, more or less, of the boundary of the squares which are covering sigma, okay? And what we do, we always extend the homeomorphisms, which will be extended in such a way that they map the square, okay, inside the polygon that is obtained after the piecewise linearization of the injectifications, okay? So in particular, if this grid is fine enough, okay, your for almost every x, fk of x will be very close to f of x, okay? As soon as f tilde of x was the singleton, okay? So, so basically, you can always construct the homeomorphisms outside sigma and also inside sigma, because they will also, the image of these squares here, sorry, if this is a square and this is, I want this connected part to be the image of this one. Okay, and this one is very close to what the original function was doing. Maybe the original function was collapsing, but still this injectification and the piecewise linearization of the boundary was done in such a way to stay very, very, very close to the original curve. Okay, and so from what was the original image of a point inside through F, the new image through the homomorphism that I'm building will still be here inside, and so they will be uniformly close, okay? So this means that any homomorphism that I build that does this job on the grid will be strongly L1 converging to F, okay? I told you outside sigma, I will not tell you in detail how to do that because it's already contained in the De Filippis Pratelli. We are able to approximate strongly, okay? Inside the squares, the bed squares of sigma, we have to find a way on how to extend to define the homomorphism inside, which is matching this piecewise linearization of the injectification. And the idea is the following, is to apply the so-called minimal extension for the rotated Manhattan norm, which says the following. So now the situation is that we start from a square and we have a polygon in the image. Okay, for example, like this one. And we have just some phi that is defined on the boundary of the square and is mapping this onto the boundary of this polygon. Okay, and I need to find a way on how to extend this phi inside. I want to create an homomorphism that is defined inside the square and maps the inside of the square into the inside of the polygon, okay, into the interior of the polygon. And I wanted to do that in the best BV way possible. What does this mean? So just a comment, if I take an horizontal slice here, okay, what will be the, so through phi, I have two images for these points, right? Maybe one is here and one is here, okay? Okay, I want to construct, so any homomorphism extending this boundary value, so homomorphisms are continuous stuff, so will be a, the image through an homomorphism of this segment will be some curve inside the polygon connecting these 2 points. Do you agree? Okay. Now the BV norm is accounting for the length of the image of this curve. Okay, and so the best possible thing you can do to pay as less possible BV norm is to follow the geodesic. Okay, now if you do this on all horizontal segments and all vertical segments, you are not clearly an homomorphism. But there is a way to do this that we did with Aldo during my PhD, to construct an homomorphism, like opening a bit the geodesics in the almost optimal way. Okay, so if for every horizontal slice and vertical slice, you count, you integrate the length of the geodesic, you get a number. This number is a lower bound for the BV norm of any homomorphic extension. Okay, what we are able to do is to construct an homomorphism whose BV norm is almost this optimal number, up to an error. Okay, this is the minimal extension. The rotated minimal extension is doing this, starting not from squares, but from quadrilaterals, and not with the horizontal and vertical segments, but perpendicular segments in any direction, in the eta direction, for example. Okay? So once you fix a direction, you have a lower bound for the BV norm in that with respect to this direction and the orthogonal one. And we are able to construct an homomorphism for which the BV norm in that direction is almost optimal, okay? So I'm saying BV norm, but what I mean is the Manhattan norm, sorry, the Manhattan BV norm. So we construct on each square, we have the preferred direction given by the Lebesgue point type estimate with respect to the preferred direction granted by Alberti, okay? And we perform the minimal extension exactly in that direction and the orthogonal one, okay? So the total variation of the gradient of the deformation on a bed square, where eta is the singular direction, let's say, is controlled by the Manhattan norm, decomposed with respect to this direction. But now, since our extending homomorphisms are doing the best, okay, almost the best up to an error, then it means that the original homomorphism was surely worse. So it's, if you're lucky, it was the same. If you're not lucky, he is doing worse. So up to another error, we have this simple estimate, okay? And now, I told you that more or less, basically, your original homomorphism on this bed square is just doing singular part of the gradient. The absolutely continuous part is very small. So this, the totality of the gradient is basically just the singular part. So up to add another error, you're just the singular part here. And which is clearly smaller than the whole gradient there, okay, on the square. And so putting these things together, we have this chain of inequalities. Clearly, Fk, I said it before that Fk is converging strongly in L1 to F by construction because we can take a very fine grid. So in particular, it's weakly star converging. The total variation is lower semi-continuous with respect to the this topology. And so this inequality is clear. Now, then the lim-inf is always smaller or equal than the lim-sup, but now the lim-sup by our construction is the lim-sup of sigma is the sum over all the squares in sigma of these guys, which is controlled by 1 plus epsilon errors of the total variation of f on sigma here, okay? And so this chain of inequalities are just equality. We have the strict convergence on the bed squares. Okay, so we are approximating the whole strict, singular part on the gradient there and strongly the absolutely continuous part outside. I have some open problems, but I'm very sorry, I went a bit over time. So I just leave them here and I thank you for your attention.
Are there questions? Maybe quick.
Is there any hope of getting compactness in these topologies?
Sorry.
Is there any hope of getting compactness in these topologies in some realistic settings?
In some
realistic settings?
I don't know. No. Let's say we're trying to study homeomorphic relaxations of the energy functionals I mentioned before to see whether we are able to recover more or less the models introduced by Henao and Mora Corral, because we have the same type of singularities, but that we are very far from there. And also no.
Other questions? Okay, if not,
No.
we thank again Emanuela.
Thank you.